I suppose I ought to introduce myself. I'm Dr. Bly, and I've been doing this for several decades. Not teaching, mind you, I was in research first. Agricultural research primarily. My PhD is in agronomy. Does anybody know what agronomy is? Most people don't. It's a combination of crops and soils. So I worked in soils myself. But I got enough chemistry, graduate level chemistry credit, so I could teach this course. So let's see, where do we start? Is everybody familiar with, you access Brightspace without any trouble, correct? No problems with Brightspace, okay. So you got a copy of the syllabus, and I think what I'll do is I'll go into Brightspace and show you where the syllabus is. Or have you rummaged around in this course in Brightspace yet? No? Okay, well, let me show you how that works. Okay, so let me share. By the way, we're Zooming the class because I record it, and Zoom allows you to record, but then I take the videos that Zoom produces and I reprocess them for quality and mistakes. Dead air, I chop out the dead air, and then I post them usually within 48 hours of the class. So by Sunday evening, this one should be in Brightspace, and I'll show you where that is in just a second. Let's see, I need to get into the browser. Here we go. System response is painfully slow. Of course, I'm probably not telling you something you don't already know. Come on. There we go. I assume, yes, it's sharing. Okay. And I don't see anybody else zoomed in. It's supposed, this is a face-to-face class, but let me know in advance, and you can zoom in if you have to. You know, if family or work issues get in the way, you can zoom in, except for the labs. You've got to be here for the labs. Right, and we'll talk, I'll show you where those are in just a minute. Okay, so right now I'm in the Zoom panel where you connect with the class if you do Zoom. Let me go back. Well, y'all know how to get to Brightspace, so I'm not going to do that. Let's go back. Here, see these breadcrumbs right here? That helps you go backwards selectively. So I'm going to go back here, start lessons. Actually, I should go even further back. Let me go back to, let's see, where is it? Course home, right there. So when you pull up the course, this is what you're going to see first. You'll just see a welcome, and that's about it. There's some other things down here like deadlines approaching. As an instructor, I don't pay much attention to those. And then to find the course, if you don't have your course up, then you go to this waffle and find the course there. 202302 is this semester, and then you look for 203. Okay, does everybody see it back there? It's kind of fine, small print. Okay, so we're already in the course. You'll find everything you need in the course, except for your grades, right? As a student, let me tell the system I'm a student, and it'll look more like what you're going to see. There we go. You can go to your grades here, and then I'll post the grades as soon as I've got the exams graded or the labs graded. I'll post them in this grade book so you can see them. And there will be a, might as well call it up. There'll be current course average here at the top. I produce the average myself in an Excel spreadsheet, so I have more control over how things are counted. If we need to make adjustments, it's easier to make adjustments in the spreadsheet than it is to make adjustments in the Brightspace black box that they call a grading system. It's just it's a mess. I don't think there are any learning management systems that do it right. So I post these manually. So if you want to know what grades go into that average, you just look down there and see the grades that have been posted. Only the grades that are posted go into the average. So if you've completed an exam or completed a homework and the homework grade doesn't show up there, well, there are two possibilities. Either I haven't graded it yet, or you think you submitted it and you didn't, right? That could be a problem. But that's where I'll put the course average. And there are 2 extra credit assignments that are available. One is in this first exam section, and that's what this handout here in this corner is, getting to know the periodic table. That's an extra credit. So you're probably wondering how much the extra credit is worth. Well, it's worth 1/4 of an exam. So it's a pretty substantial amount. And the other extra credit is also a 1/4. So both together, that's a half exam grade in weight. Okay. By the way, stop me anytime that you're not hearing me or you have a question. Okay. Otherwise, I'll just keep rattling on. Okay, so let's go back. To find anything else you want, go to content. And that's going to be common for any Brightspace course. You go in, content is where you start. But I subdivide out, they've got a table of contents and you click on that and it kind of resets everything. But I go in here and most of the information you're going to need, except for a couple of things down here, is start here, lessons and resources. So this first module is the syllabus, and you've got my schedule, which is that really colorful handout with the reds and the earth tones and the greens and the blues. That tells you where I am at every time during every period of the day. If there are any blank spaces in there, that means that I'm available. I'm just not zoomed in. You see those, the red ones. Let me call it up here. Schedule. Here we go. So this will give you my schedule. These with yellow highlights and the maroon background, those are my office hours, and my office hours I do at New River. So you're not going to travel to New River. It's 73 miles from my house to here, unless you live in that direction. But during my office hours, I also Zoom them. So you can connect with me. Here's my Zoom ID right there. And if you need help, then you can Zoom and catch me there. Or if those times, let's see, on Wednesday I've got 2 Zoom sessions, Thursday I've got 1, and Monday I've got 1 that runs late. I do that one from home. But if those time slots aren't convenient, if your work schedule or family gets in the way, we can set up a Zoom session independent of those. Okay, I'll just send you an email reply with a link, and you just click on that link and open up the Zoom, and we can discuss any problems. Otherwise, I'll be in these courses here. These are all face-to-face. I've got some online versions, but any of these white sections, we can set up a Zoom session there. We could even do it on the weekend. I'm not opposed to that. Okay. So let me go back. And you've got a copy of the syllabus. This is another office hours link. Those Zoom office hours, this is where you go find the link. Right. So if you've got a computer and you have access to Brightspace, you can click on that, and that'll take you to the Zoom session where I'm in my office hours. But if you don't have your computer with you and you want to do it with your smartphone, then you would have to set up your own Zoom, open up your Zoom app in your phone, and type in that code, that ID number. I don't have a passcode on my personal So anybody can come up. I've never been bombed before, but it could happen. Okay, so I'm not going to spend a lot of time there. We will look at the syllabus. Let's go ahead and look at the syllabus here. This is as good a place as any. So let's scroll it up a little bit. All right. You're familiar with the way they put the syllabi together now for all the courses. They come in 3 sections, 3 parts. The first part and the last part you can pretty much ignore because they're dictated by the school. They have to be in the syllabus. The part that's specific to this course is part 2. So I'm going to go ahead and scroll down to part 2. Right. And let's keep going. There we go, part 2. So that gives you my contact information and my Zoom ID again. Tells you where my office is. I guess you could consider this my office while I'm here on Fridays. There's also another what do you call it? A link address for my Zoom sessions, my office hours. So here's where we get to the meat of the course. This is the schedule, the course schedule. And I've highlighted in yellow the things that are really important, like due dates and exams. So here we have on the 10th of February is going to be our first exam. And by the way, I didn't put it in here, but those extra credits, the first extra credit is relative to the first exam. So it's going to be due the same time as the exam is due. Okay, so if you turn it in with that exam, it'll be on time. And the second one that I'll hand out when we get through with this exam will be due on that date for the second exam here. But more on that later. So what I've got here is dates on the left, and there's some of their non-Fridays. I put those in because those are important dates that you may need to be aware of. Mid-semester grades are due on Monday, the 6th of March. Right. If they're grayed out, that means there's no activity in that slot. Right. And then Thursday, the 30th of March is the last day to withdraw with a W. And spring break, we won't meet on then, 7th of April. School will be closed. And then the final grades are due on the 8th of May. Okay, one other, before I go too far. This Friday, the 3rd of March, I have a conflict in my schedule. The president of New River has scheduled our, you could call it a convocation. We call it a faculty staff institute, where everybody mandatory, you've got to be there in person. So I have to be absent that day. So don't even come unless you have another class here. We'll just skip over that day. So that'll give you some extra time to absorb the material that we've covered in chapters 4, 5, and 6 here. And then when we come back on 10th of March, when I will be here, we'll do a review. So I've scheduled it so we have a full class period, a lecture period for review. And at that time, you bring your specific problems to class and we'll iron them out then. If you can wait. If you can't wait, then we can Zoom a tutorial. But you'll find that that's the pattern. We'll have a lecture, and then we'll have a review session, and then the next week we'll have an exam. And right after that exam, we'll start the next section. And notice when we do that on exam days, there's no lab, right? Because there's too much to do in one day to have all that and a lab. So there won't be a lab on the day that we have an exam. I put the due dates for the lab. So the safety practices in the chemistry lab is one handout. That's considered lab number 1, and it's due next week. The pattern is when we finish a lab in here, then the report for the lab is due the next time we come in to do another lab. Right? So the lab number 3, notice down here, lab number 3, laboratory techniques, that won't be due the next week. It'll be due the week after, because the week after that is an exam. There's no lab. So it's due the following week. Okay, that's the pattern. Okay, does everybody have their textbook already? Yeah. Okay, good. We'll talk about other stuff you need in just a minute, but I wanted to get through this. So it's the structure of the course is well explained. We're going to have 10 labs, which is plenty for a 15-week course. And 4 exams. And there's no final exam. There's no time for a final. I don't have time to go through a review, which you deserve for a final, and then have the final also. So the last exam will be during the final exam week on the 5th of May. Okay. And that's all we'll do that day, I think. Yes. Well, should be all we do, because if we try to do a lab on that day, when are you going to turn it in? Right. We don't meet the next week. Okay. So I grade on a 10-point scale, right? Anything over 90 is an A, and that should be your goal, right? Get that A. It is attainable, believe me. Your exams are worth 70%. Average all your exams together, and that's 70% of your grade. The labs are worth 30%. So since there are 10 of them, that's wrong. 11, they're not 11. Okay. Good thing I haven't sent that to management yet, so I better correct that before I do. There are only 10 labs. This was an earlier version. I forgot to make that correction. And all this other stuff is for the benefit of, well, that stuff is for assessments. Right, so you don't have to worry about that. Now, this little section in here is optional. Your textbook has end of chapter problems. Right? So what I've done is I pulled out some of those problems and numbered them here for each of the chapters under each exam. And those are good review problems. Right? But since I produced this, I've also produced another document that I think might be more useful. And that's the one that you picked up on the far end over here. And it says at the top, review for exam 1. And it looks exactly like a multiple choice test. And I do that on purpose because some of my students like to take that and actually treat it as a test. Just run through it and mark your answers and then grade it. Now, I didn't give you the grading key. It's in Brightspace. Let's go back and find it. Let's go out here. That's all we have to see here, I believe. Well, except for the labs. You have your copy of it out. Yeah, it looks exactly like an exam. And the Brightspace in the same place that the review document's located in the exam 1 module. Come sign in and grab one of these, each one of these, okay? Excuse me. There's a key. I tried printing out lots of stuff in the past, and I printed out too much and crashed the printer. So I just print out the non-key, the one with no answers in it. So you can find the answers in Brightspace. We'll come to that in just a few minutes. Before I leave the syllabus, I want to talk a little bit about what you need, other things you need for the lab besides your textbook. You'll need a calculator. If you don't already have one, you need a calculator that is labeled scientific. And I just learned the other day, a student showed me their calculator and asked me if it had all functions they need. And it did. It didn't say scientific on it. They went a step up and got a graphing calculator. Those calculators will also have the functions you need, but they're a little pricier. So if you don't need all that power, you just get a $10 at Walmart calculator, and if it says scientific on it, it'll do everything you need. I put the functions in here just so that we'd be sure you could check it and see, like logs and exponents and scientific notation and floating decimals and all that stuff. Now, if you have a calculator in your cell phone, you can use it anytime but on the exams. Cell phones are way too smart. So for exams, you got to use a regular calculator. I keep one spare for students who run off and leave theirs at home. That's the arithmetic type where you say 1 + 1 =. If you punch in the numbers and do that, you don't want to use mine. It's a reverse Polish notation. In this one, you say 1 enter 2 plus, or 1 enter 1 plus, you get your answer. So it's more efficient, but it takes some getting used to. But I do keep an algebraic calculator as a spare for students that are desperate. Okay, so there's a note on lectures and review sessions. They're all recorded and posted. I said 24 hours here. It's as busy as I am this semester. I'll be lucky to get it in 48 hours. Should be in by Sunday. Electronic devices. Just be considerate of everybody. If you've got a cell phone and you're expecting a call, or you have possibility of a work call or a family call, just put your phone on vibrate. And if it vibrates, just hop up and go outside and take your call. And that reminds me, I better check mine. So I don't want it going off. When I told you can't do yours, and then mine acts up, that wouldn't be fair. I've got a little app on mine, and I got a schedule. I put my schedule in here, and it silences my phone automatically for the times when I'm teaching or doing other stuff. I don't want to be interrupted. Okay, regular exams there, lab reports. Okay, the lab reports, we don't have any formal lab reports in this course. So when I hand you a hard copy, there are places in there to write answers, to do calculations, to draw conclusions. And it varies from handout to handout as to how they're arranged, whether they're just an item with a line where information goes, or maybe a question with a bunch of lines, or sometimes it's in a table. But you don't have to write a formal report in this course. It's I think it's beyond the scope of this course to have you do formal reports. Has anybody ever done a formal lab report before? No? Okay. It's a good skill to develop, but it's beyond the scope of this course. Let's see, extra credit, bonus and extra credit. You have those two standalone extra credit exercises, one for this exam and one for the next exam that I'll give you later. And then occasionally during the exam, I'll have extra credit questions available. So it's possible to get more than 100% out of an exam. Okay, there's another copy of my schedule. And then we get into part 3. I guess this was useful. It's got information on the textbook and the lab book. Has anybody bought the lab book yet? It's in the bookstore. If you didn't buy it, don't worry about it. The only reason I leave it in there is because I've taken 2 or 3 of the exercises out of there and modified them for the class, and I just don't want to run into copyright infringement problems. So that's why I have the students buy that, but don't open it. leave it in cellophane and maybe you can sell it back. Or sell it to a student that is coming along taking the same course. And a lot of my other exercises I bring from New River that I've already developed. And, why reinvent the wheel? I've got good exercises from there, so I have them done here, and I have cardboard boxes, and I bring all the stuff with me that I need, glassware and your and other items that are already here. I don't have to bring those, and we'll talk about that later, because in the right hand cabinet, those two tall doors on the right, they're slide out buckets, right? And those will be assigned to groups. You need to have at least one lab partner. See, we've got 2, 4, 6. Well, we have 9 people, so I guess technically if everybody shows up, we'd need 3 in one group, because working alone is not a good idea. For 2 reasons: for safety and for problems. If your partner's here and you're not on a lab day, then you can at least get the information from your partner. You're not chronic about it, right? Your partner might get irritated if he or she has to show up and you never show up, and that just wouldn't be fair, would it? Besides, I'd notice it. Okay, so, and the rest of this stuff is for assessment of the course, so you don't need to worry about that. It's there to satisfy the Higher Learning Commission so we can keep our accreditation. Okay, let's see, what did I do? There, okay. So let me go back to the top and stop wasting time. So that's syllabus, module, and now we come down to if you want to attend, if you check with me and let me know that you've got a problem with, say, travel or conflict, and you want to Zoom the meeting, right? How far do you travel? Each of you travels. How far do you have to travel? 30 minutes. Okay. 30? 5? You're close. Okay. 5? Okay. Oh, okay.
But as long as it doesn't snow.
Yeah. We'll talk about that too, inclement weather. How about hour and a half? Are you from out of state? Okay. And 30 minutes. Okay, so some of you have to travel a good bit. So maybe what we could do is make arrangements for just across the board on days when we don't have a lab. You can Zoom the course and take the exam online. I have to talk about how to do that. That'll come up. I'm working my way down, so it'll occur. This is that optional homework. I don't have graded homework. There's just no time to grade everybody's homework. I don't have an automated system to do it. At New River, I have my textbook is from Cengage, and they have a nice homework app, and my students go to Cengage and do their homework, and it's automatically graded. So that's good, and it gives them practice. But for this one, that's not an option. Okay, so here are the exam modules. So everything you need for each one of these exams is in here. So here's exam 1, and PowerPoints here. If it gets too busy, just hit this collapse all right up here. See that? Hit collapse all, and then you open one up if you want it. So here's PowerPoints, open it up. There's chapter 1, 2, and 3. So if I click on 1, you'll find that the PowerPoints come in 3 flavors. These are PowerPoint slides. So if you have Microsoft Office, and you can open these slides up and view them just like any PowerPoint presentation. If you don't have access to that, or you're using a device that doesn't have Microsoft Office on occasion, then you can look at the PDF version here. All you need is Acrobat Reader. Right, does everybody have one of those on your computer? Okay, good. But it won't have any of the animations. It won't have any embedded videos. So what I did was I came up with this one, which is an HTML version of the course. I took all the PowerPoint slides and I got a conversion program that'll take them and put them into this format. And all you have to do is go into your, from here, you click on that. And it's messed up. I was afraid of that. It continuously scrolls. All right, I'll try to fix it. Ideally, what it will do is the HTML version embeds all the animations and all the videos. So you can view it from within your browser. I don't know why it does that. I know what I need to do. Okay. I don't need to expound the reasons, but if I can remember and get the time, I'll fix it so it won't do that. Continuously scrolling. I used a program that was cheaper than the Cadillac version. The company produced one, and this happens occasionally. It just keeps scrolling, and I've contacted tech support about it, but they've never fixed it. So I'm gonna have to, now I've got the Cadillac version, so I can fix it. But also, you've got the videos. So the videos are recorded along with, because I'll share the slides and then I'll process them in the video, and you'll have me on one side and slides on the other side. So you'll see everything with the processed Zoom video. What I do is as I position the link in here, let me go back. Back. Let's do it like this. There we go. That's not what I meant by back. Let's go back here. All right, let's go over here. Come on. No, let's go here. PowerPoints, here we go. I've got Zoom recordings in here already from previous semesters, right? So if you don't want to wait for the one that we produced ourselves, you can go back and look at some of these. I'd start with the most recent one and look at that for review. It won't have the same warmth that our video will have, right? It'll have a previous version, and I talk differently. So it's not exactly the same, but it does cover the same material. And but what I'll do is, these Zoom recordings are archived. So what I'll do is, for the Zoom recordings that we produce, I'll set them out independently. So they'll sit in here right in that gap. There's your extra credit periodic table. That's the one, this one right here, getting to know your periodic table. And the instructions are on the first page, and the blank periodic tables on the second page. You just fill it out according to the instructions and turn in both pages, because I use that front page to grade. Okay. Here's your review document. There's a review quiz. I forgot I had that in there. So if you want to drill this quiz, it'll grade it and tell you which ones you missed, and then you can go back and work on your weak spots. But I won't ever see the grade. I've set it up that way. I don't want to see those grades, because they're not, I don't average them into your final. These are some other documents. Do I have the, well, let me see. Hold on a second. Oh, I think it's this one. Nope. It's the other course. Here we go. So So I don't have to keep walking up there. Credits. Where is it? No, not extra credit. Your review document. Here we go. Chapters 1, 2, 3. Okay, that should be in here. No, that's a bright space quiz. Okay. I wonder if I missed putting that in here, because you're going to need the key. Let's see here. No key. I think I know what I did. Yeah. Okay. I understand. This document is those 3 documents in one place. Okay. So if you lose that one before I have a chance to give you a replacement, then it's going to show up in 3 different documents. This document only covers chapter 1 that's in that document. I think. Yes. So the others, this chapter 2 and this is chapter 3, those 3 documents, I put them together into that single document to hand out. And then the key for each one, each chapter is going to be here below it. Okay. All right. Let's go back. Go back again. Here we go. Breadcrumbs. All right. What else is in the module? Because each module is structured exactly the same way. So there's module 1. Then here's the extra credit, and here's the exam. Yeah, I have changed the due dates on it. So if we do it this way, I don't think the exam is available yet. No, it's not available. So I'll tell you what. Nah, I better not. When it becomes available, does that sound reasonable? Do you like to sit in the class and take a paper exam? You prefer that? Yeah. Okay. The advantage of taking a paper exam is I will grade it before you leave the class, and you will know what you made on it before you finish that day. I do that because you want to know as soon as possible where your weaknesses are, where you work on them. Because chemistry is a cumulative course. In other words, each new topic builds on the past, some more than others. So if you know where your weaknesses are, as soon as possible, you can fix those so that they don't interfere with learning the subsequent material. That's why I like to have them graded before you leave. So if you can, come to class. If you can't, let me know that you want to do it online, so I'll be ready for it. In fact, if you're going to submit it online, I guess I better change over to instructor. Now I'm going to have to go back in the course. Okay, there it is. Okay, so when you click on it, the document's going to be here. It's a PDF file, and it looks exactly like the paper copy that you would get if you showed up face to face. So you fill it in. It's a fillable form, and you can open it up in your Acrobat Reader, fill it in, and you can actually save it. I've got the full version of Adobe Acrobat, and when I created these files, I saved them as fillable forms that can be saved. So normally when you open a form and you fill it out, once you shut down your program, you can't save it, and you shut it down and all your answers are gone. But this way you can fill it out in your reader and save it. And then you submit it right down where it's supposed to be a place to submit. Oh, I'm an instructor. As a student, you'll see a place in there for submission. All right, so you just, once you've saved your work, you go to that one and you click on add attachment, I think, something like that, and then go find it, and that's where you submit it. And it'll send me a notice that you've submitted it. Okay, if that's agreeable to everybody, then we'll do it that way. If you've got to travel hour and a half, you can Zoom the course and on that day take the exam, since we don't have a lab that day. All right. But if you do it that way, the deadline is 11:59 that night. Okay. There's no option for midnight. It's 11:59. And you've probably seen that in other courses, I guess. Okay, so let me go back and see what else there is, if anything. I better go back to being a student. Let me do that. Because if I don't do that, then I have had happen in the past. If I go through there and demonstrate to the class as an instructor, I see stuff in there that you're not going to see. And if I get to thinking that those items are available to you, but they're not. So students that have their laptops with them will be in there as a student, and they'll see that I don't see it in mine. I have to correct it. So I try to go in as a student now. Okay, laboratory exercises. These are where you can get copies of your laboratory exercises if you stay home for the exam. I usually hand out the hard copies the week before. So if there's an exam there and you're not here, then I won't be able to hand it out. So what I need to do is remember to hand it out when we're actually having a lab in here for the next one. Otherwise, if you stay home that day, you wouldn't get a hard copy. You'd have to print out your own copy. And I mean, as much money as, I don't know, most of you on getting financial aid, most of my students do. Somebody's paying a lot of money for you to take this course. So I think you deserve to have me print it out for you. In fact, I print these at New River in Beckley because I like color and they don't print color here. All the printers that are available to me are black and white. And that just doesn't look the same. Okay, so here are all the lab exercises. Let's go down to say, here's the first one, lab techniques. This is the first time we're actually going to come into the lab and start working with stuff. And by that time, what you need to have is a lab coat, knee length, at least knee length. We have safety goggles or eyewear protection, but they're kind of old and they've been used over and over and over again. They're probably scratched. So you may want to invest in a pair of your own. And you don't have to get full goggles unless you just want to. You can get those wraparound polycarbonate glasses. They look like glasses. They look like sunglasses, only they're not tinted. You know what I mean? So by the time we come in for lab number 3, you need to have your lab coat and eye protection if you want it. And we provide the disposable gloves. And they're non-latex, right? So you don't have to worry about allergies. So here's where you would find the document for lab techniques right here. Just click on that. And then there's a place And then you have to click again to get the document. And then also there's a place in there to submit your work. So if you submit your work in person, that's perfectly all right. Hard copy is great. But if you forget it or you are absent for some reason on the day it's due, you could submit it in here also, just like you would your exam. Okay. I've also got a demonstration for the videos. I produced these videos back when we were in the COVID panic and they wouldn't let us come to class. So for my classes, I got permission to come into the lab by myself. And I did the whole lab myself. And I had this little GoPro camera on my head. It wasn't really a GoPro because I can't afford those. It was a knockoff. And recorded everything that I was doing. And then the students had to view the video and gather the data and observations from the video and complete the report. So it wasn't the best of worlds, but it was the only solution I could think of that would at least give you a visual impact of the exercise in lieu of hands-on. There's no substitute for hands-on in the lab. Okay, so today we're gonna look at, as soon as I've shut up and get through the 2 lecture chapters, we're gonna do a little bit on safety, and that's all there is for today in the lab. Next week, if I have time, we'll do a little introduction of next week's lab is graphing techniques. That's actually graphing techniques is what you do with the data after you get it from a lab. How do you present it? And this, you present it in graphical form sometimes. And this is an exercise in how you present your data in visual form, in one type of visual form. So more on that later. Sure you don't have any questions? Or are you still in shock? Seen it before. Chemistry anxiety syndrome, I guess you call it. Okay, so if you don't have any questions, what I'm going to do now is stop this share and ask myself if I've covered everything I need to before we get into the materials. Let's see. Let's review. Oh, I didn't say anything about that periodic table. The one with the red boxes in it. Okay. That periodic table let me just yeah, I guess I ought to put it up on the screen. So while I'm talking about it, it'll be recorded. So let me go in and get that one. In fact, it should be in Brightspace. Let me go back and share. That's the best way to go. No. Close that. Share. Let's go back here and go back in the course. Share. Okay. So if we go down to, let's see, should be in this module. It should be exam 1 module. Extra credit, periodic table, reviews. It's not there. Okay, I better make myself a note. Well, I don't have my Post-its. All right, I'll make a note here on the syllabus. Know these. Brightspace. I need to put that document in Brightspace too. So let me stop this share and open that document in Word, and then I'll share that. Okay. Open. Browse. Come on. Here we go. Let's see here. And here. Let's see here. Come on. Respondents. It's in here. Supplement. No, not getting to know. Know these. Here we go. See, to give me a preview. So I'll be sure I open the right one. Yeah, it's close enough.
It's in there. It's under table of contents.
Oh, it is in.
Yeah,
Where is it?
table of contents. Click on it and it's the third one. Do that one.
Oh, okay. It's not embedded in the modules. Okay. Well, let me share again then, so I can talk about it. Come on. Here we go. Okay, so I need to go back to table of contents. I don't see it. This one? Contact information. I don't see it on mine. Am I looking in the right place? Contact information, resources. Oh. Oh, okay. It's not on the sidebar. Oh. My excuse is I have an old brain. Yeah, February 25th, I turned 70. So it kind of goes without saying. Anyway, what you see is a periodic table with all the symbols and some other information and red boxes. Any group or single element with red boxes around it, I want you to memorize those symbols. What the symbols, the element that the symbol stands for. So if you get a symbol, you know the element name. If you get an element name, you know how to write the symbol. And only the ones that are in red are the ones you need to memorize. There should be on the order of about 60 of them. There are 118 elements in the table, so it's roughly half. And the best way I found to do it is get yourself some 3x5 flashcards, index cards, and make out your own flashcards. You just put the symbol on one side and write the name on the other. Notice there are no names here, so you got to look them up. And when you make those cards, that starts the memorizing process. And then you just run through them. Has anybody ever memorized using flashcards? Right. Oh, well, yeah, you go through them and say, get that one right. Yeah, this pile. Get that one wrong. That pile. And you just keep working on the wrong ones until they're all in the right pile. And then you go back and do it again. That way, you'll know the symbols, and you got to know the symbols. These are the alphabet of chemistry, knowing those symbols. Okay. My goodness. I've already gone an hour. Let's see if I can get 2 chapters in the next hour. Maybe, maybe not. Okay. So, yeah, I was checking to see if I'd missed anything, and I think that was the last. That was the last one. So now I'm going to get my PowerPoints out. go. And let me just check how long they are. Takes a little effort. The second one's a little shorter. Okay. All right, so let me open up my PowerPoint slide set, and we'll start with chapter 1. And brown. Down. Here it is. Here it's spring. 3. All right, so let me go down chapter 1. There's chapter 1 and chapter 2. Okay, so let me open up both of them while I'm here. Okay, there's 1, there's 2. All right, so now I need to go back and share. And chapter 1. Come on. There we go. Okay. So let's go to from the beginning. There we go. All right. Put myself up there in the corner, so I won't interfere with the slide set. All right. If I grimace, you see a funny look on my face, not normal funny, but when associated with pain. I've got a spider bite on my finger that's abscessed, and it is extremely painful. I've got it suppressed right now, so it should be okay unless I whack it on something. He also caught me on the nose in my sleep, bit me on my finger and my nose. I wish I could find the sucker, but that's not chemistry. So let me get my, let's see, there, get that out of the way. All right. Chapter 1, basic concepts. What we're going to do is in this chapter, try to orient ourselves to the way scientists look at the world. For centuries, people have been wondering how things happen in the natural world. And for various reasons, some were just curious and some had the wealth and the time to do it. But some wanted to know how the world worked so that they could profit from it, right? Profit motive is as ancient as humans are. So we're going to run through this list. This outline is just there for, it's not something we're going to spend time on, but those are the topics that we're going to cover. So in specifically chemistry, what is chemistry? Well, chemistry is the study of substances and how they change from one to another, the transformations that they undergo. And when we say transformations, we're talking about a substance that changes its identity. Its physical and chemical properties change in the process. That's what chemistry approaches. And chemistry is a very broad subject matter to study. It's branched off into dozens of different fields. And in fact, my afternoon class, we use a textbook that's called Chemistry, the Central Science. And that's not far from the truth. It is central to almost every other science. Now, of course, if you talk to a chemist about biology, a chemist will say biology is just applied chemistry. But if you talk to a physicist, they'll say chemistry is just applied physics. And I've never talked to a mathematician, but I'd be willing to bet the mathematician says, you're all just applied math. right? You can break everything down into ones and zeros, so to speak. But that's chemistry. We study any type of substance that changes into something else. And in fact, many of the advances in chemistry came from the physics side. So when we get to studying gases, the introduction of gases as a study is going to be almost purely physics. And only when we get a grasp of the physics of gases can we use what we know there to help us understand chemical reactions involving gases. So what's matter? Right? I remember in grade school, they defined matter as anything that occupies space and has mass. And that's a pretty good definition. That's matter. It could take the form of living or non-living materials, right? Could be what I studied in my PhD is soils, right? Soils are actually a combination of living and non-living, right? If you have a cut on your hand and you play around in the garden with a cut on your hand, might get infected because there are lots of organisms there in the soil that you don't see. We breathe in microorganisms. Every breath you take, you get a bacterium usually. And your body's immune system is there to take care of that for you. We even engineer materials that we use every day now. For the longest time, anything that you used in your everyday life was just a modification of something that already existed. Like they build your houses out of stone or wood, or then we started modifying materials by packing clay together and firing it. Actually, before then, we just mix a little hay in with it and let it dry in the sun, make adobe bricks, right? The problem with that is when it rains, it washes your house away. So we learned to fire them in an oven, and then the bricks were impervious to the weather, right? So man has been modifying materials and causing chemical reactions for thousands of years. But it's only recently that we've managed to engineer materials at the molecular level, in particular plastics, right? Many of the things that we use every day, like this material on this table, that's not real wood. It's got wood grain imprinted on it, but that's a polymer. It's a plastic. We understand chemistry insofar as it allows us to engineer our world, and that also extends to engineering the kind of energies that we can use. Right? For the longest time, we just burned what was available. Right? Some societies still do that. In the third world, they'll burn wood, and they've cut down their forests. I mean, they've completely denuded their land surface and turned it into desert, because now the soils don't have any plant life to speak of living in them and can't hold the soil, can't hold the moisture. So they've turned their land into desert. Spain used to be covered in forests back in the Middle Ages, but they started building ships, right? One group of ships in particular, the Spanish Armada, tried to go up and pick a fight with England. Of course, the nature said, no, you don't, right? It destroyed their ships in a storm. But that type of using up your natural resources for building purposes is one thing, but for fuels another, right? If you build something with wood, it's going to be around for a while. But if you cut down a tree and burn it, that's it. It's all over. So they use wood largely, or twigs and that type of material. Some societies still use animal dung, dried dung, to fire, to create their campfires and cook their meals. But we've moved on from there in the developing and the developed world. We use mostly fossil fuels now, oil, gas, coal, and some nuclear. Right? Nuclear more in some countries than others. But chemistry has been instrumental in allowing us to do that. And most of our cars run on fossil fuels, like gasoline. I think I paid $3.20 in Beckley last time I filled it up. And then I came through Man, and they're selling it for $3.09. You know, I got to fill up on the way home. So the universe itself is composed, can be broken down and said to be composed of either matter or energy. Right? That covers everything for our purposes. Right? You talk to some elite highbrow physicists, and they're talking about dark energy and dark matter. How do you know it's there? Right? It's dark. You can't see it. Right? You can't measure it. So it's theoretical. Okay. We're going to have to skip these things or I'm not going to get finished. All right. So we're going to look at the physical states of matter. In fact, when we start putting elements and compounds into chemical reactions and we write the expressions, sometimes it's useful to also add in what form is this, right? So if we write water, is it in the liquid form like that, right? Or is it a vapor, right? Is it a gas? Those are the way that we say what state it's in. Or is it ice? Is it a solid, right? Or if we put table salt, if we spill it on the table, right, it's in what form? It's a solid, right? But if we dissolve it in a glass of water, it's in aqueous form, AQ. Right? Those are the abbreviations we'll use for different states. Now, the only ones we're talking about here are solid, liquid, and gas. Right? We'll get to aqueous later. So we need to understand what are characteristics of these. Solids, their structure is such that they can retain their shape, and they have a definite volume as well. You can set that solid on the table and it'll stay there as long as it doesn't react with anything in the air or react with the table. It'll just sit there, and it can hold its own shape. A liquid, on the other hand, can maintain its own volume, but the molecules in there are not rigidly associated with one another. So they move past one another, they slide past, and it flows. So if you put your liquid on the table, it'll just go like that. It needs a container. So no definite volume for a liquid, but no definite shape for a liquid, but definite volume. And then gases have neither. A gas has an indefinite shape and an indefinite volume. You have to have a completely closed container to say that you have this or that gas in that container. And if you put a little bit of gas into this size container, it will expand to fill the whole container. Okay, just some examples. Right, you got looks like an Eisenhower $50 on the left as a solid, and then the middle we have a liquid. I don't know what that liquid is, colored water maybe. And in the beaker on the right, notice it's got a cap on it because that looks like maybe chlorine gas. And it has to be contained, completely contained. Okay. What are the factors that control the state of the matter, right? Whether it's a liquid, gas, or solid. Temperature is probably the most important. we raise the temperature of a solid, eventually it'll melt, turn into a liquid. We keep raising the temperature, it'll turn into a gas, right? If we cool it down, we can go the other direction. If we want to influence the state of matter, we can also change the pressure on it. And this is particularly effective if it's a gas. You pressurize the gas and you squeeze it down, Well, we're going to learn later that it gets hotter as you do that. And anybody knows, have you ever pumped up a tire with a hand pump, right? And then when you get finished using it, quick, go down to the bottom where the outlet is and feel it. It's hot, right? When you squeeze that gas, it gets hot. So if you're going to squeeze the gas and you want to make it into a liquid or even further into a solid, then you got to do something with that excess heat. If you don't, it's just going to stay a gas, right? So when we condense gases into liquids, it's usually a two-step process. You compress it and you cool it at the same time, and you can turn it into a liquid. Or you can keep going on some gases and turn them into a solid. Carbon dioxide, for instance, right? You can go from a gas to a liquid if you compress it and cool it. And then solid, you can make it solid, right? Everybody knows what solid CO2 is, right? What do we call it? Dry ice, right? Solid carbon dioxide is dry ice. One other condition that we don't have any control over is what are the strength of the forces that hold the individual molecules together in that material, right? If there are really, really strong attractions between the molecules, then you won't have to do much. You won't have to cool it very far. You won't have to compress it very much to change its state, because they want to hold together. But if they don't, I mean, if there's no, well, I shouldn't say no, if the forces holding those, attracting the molecules or atoms together are very weak, then you're going to really have to cool it down and compress it really hard to get it there. So when you get to this place in dry ice, its temperature is going to be minus 78.5 degrees Celsius. But if you try to do the same thing with nitrogen, and you go from a gas just to a liquid, right? You're going to have to cool it down even more, because the nitrogen molecules don't attract each other as strongly as the carbon dioxide molecules attract each other. So when you get to liquid here, you're going to be at minus 195 degrees C. Okay. I used to use liquid nitrogen on a regular basis. We would freeze plant material in it. The quicker you freeze something, the smaller the ice crystals, and they don't damage the cells in the living material. So the faster you can freeze it, the better. Anyway, those are factors that influence the states of matter. So the physical states are solid, liquid, and gas, and those are the only ones we're going to deal with. There are other states that are kind of exotic, like plasma, right? Ionized gas. You can get that on the surface of the sun, or you can get it in a muffler shop, right? Anybody seen a plasma torch? Well, they cut an old muffler off, right? It blows argon through this thing, and there's a huge voltage arc across there, and it turns that argon gas into plasma, ionized gas, and it blows it at your tailpipe and just cuts it like a hot knife through butter. Okay, let's look at the different properties of matter. These are descriptive terms that help us identify the materials, a property. The properties come in two flavors, either physical or chemical. And this largely describes the potential, right? What does this substance have the potential to do? So let's take a look at them. Physical properties. Those are descriptive characteristics of the material that suggest anything that's not chemical. That's not a good explanation. They're things that identify the material, but they're not changing into another identity. Like if you say something, a color is blue, I mean, that's a physical trait, right? This 3-ring binder has a blue cover on it, right? Okay. Now, I don't know how I got that way. Maybe some chemistry was involved to get it that way. But right now, I'm just describing a physical characteristic of that cover. Something smells rotten in Denmark, right? According to Shakespeare. Or if you're driving down the road and you smell this horrible sulfur smell, you want to ask, where am I? Right? If you're in Greenbrier County, then you may be close to one of the springs over there, and it stinks. If you're not, then you may have encountered a skunk, right? But that odor is just a physical description. The states of matter, that's a physical property. Melting point, right? At what point does this solid become a liquid? Well, minus 78.5 degrees. Anything higher than that, start to make a liquid. Right? Well, carbon dioxide is not a good example, because what do you do? What happens to a piece of dry ice if you set it out on the bench? It doesn't turn to liquid, does it? It goes straight to gas. That's called sublimation. So that's a bad example. If you put a chunk of ice on the table, when it heats up above 0 degrees Celsius, it'll melt, starts to melt. That's its melting point. Boiling point, you take that same water and raise the temperature to 100 degrees Celsius, it'll boil. But remember the pressure as an influence on those states? If the pressure is 1 atmosphere, right? The pressure of the air pressure on that water at sea level, then you get 100 degrees as the boiling point. It's an interesting thing about boiling points is if you go up in elevation, like you try to boil water in Denver, right? It won't boil at 100 degrees. It boils at a lower temperature. Yeah, that's why when you cook a 3-minute egg in Denver, you better make it 3.5 minutes, because the water's not as hot. The boiling water doesn't get as hot. That's another topic. How hard is something? That's a physical property. Have you ever had a science course in high school, say? Right? Talk about mineral hardness scales. Ever heard of the Mohs scale? No. Well, different materials are given a hardness number, right? The hardest number in the Mohs scale is 10, and that's assigned to diamond. And the softest one is 1, and that's assigned to talc, right? And they have gradations, examples in between. And if you take your whatever your device is, and you can scratch the surface of one of these materials, then it's harder than that. If you go from this one, it scratches, it scratches, it scratches, it scratches, it doesn't scratch. Okay, it's in between those two. Hardness is a physical property. Okay, I'll leave that on there long enough to get it in the recording, and then we'll move on. Chemical properties. Chemical properties describe the potential for a substance to change its identity. So we're not actually describing the change. We're saying this is the change. This is a property that lends itself to the change. So when we say copper objects can turn green in air, that's a chemical change. Because you get that, have you ever seen a house with a new copper roof, copper shingles? No, they're not very common. Public buildings tend to have them more often because tax dollars can afford to buy them and personal dollars can't. But we have this, I went to Louisiana State University in Baton Rouge, and we had this one building. It was an agricultural coliseum, right? It had dirt floors and they had rodeos in there and they had other things going on. But the roof was made out of copper. And the administration decided to repair it one time, and so they just said, oh, we're just going to reclad it in fresh copper. So sure, they did. They just covered the whole building in copper, and it was nice, that bright, shiny, like a new penny. Right? The weather down there is pretty aggressive, right? Lots of rain, lots of pollution. This is Baton Rouge, with Exxon just up the river, right, spewing their pollutants into the air. And the copper surface started to weather, change. And it went through a series of different color changes. Eventually, it produces what is desirable. They call it the copper patina. And there are buildings in Europe that have been, they're hundreds of years old with copper roof on them. And the color is quite striking. It's kind of a bluish, greenish color. And it's the result of copper reacting with certain compounds in the atmosphere. Acids from the rain, sulfur, copper sulfide is one of the products that's formed. So that's a chemical property. We know that copper will react to produce this color. Let's see, let's move on to, let's see. Well, there you go. The Statue of Liberty is covered in copper, right? And it develops that patina. It's just been renovated not too long ago, within the last 10 years. So maybe it's in the process of re-weathering. So let's see if we can classify each of these as a physical or a chemical property. Iron metal rusts in an atmosphere of moist air. Chemical or physical? I'd say chemical. Rust is entirely different from iron, right? And it is a chemical change that we're going to discuss in a minute. Mercury metal is liquid at room temperature. That's a physical property, right? We didn't change its identity. We just described its potential. It's a liquid at room temperature. Nickel metal dissolves in acid to produce a light green solution. That's chemical. Yep. Okay, chemical, physical, chemical. Here we go. Now, when we talk about changes, physical or chemical changes, we're actually talking about describing the change from one thing to another. In a physical change, the identity of the substance does not change. In other words, when ice melts to liquid water, it's still water, right? The identity did not change. Or if we make a gas out of it, it's still water. That's a physical change. Chemical change, on the other hand, is where the substance actually changes its identity. In other words, iron becomes iron oxide, rust. That's a chemical change. We describe the potential, the chemical property. Iron has the potential to be rusted in moist air, but we didn't say anything about the change yet. When we actually say iron becomes rust, that's a chemical change. I grew up in Atlanta, and there was a building down there. Some architect thought he'd be smart. It was called the Omni. And it was supposed to be a sports arena and some other things. And the Atlanta Hawks played there, and the Atlanta Flame hockey team played there. And some architect had hit on this material. They didn't want to have to keep repainting it. So he said, okay, use this material. It's a form of steel that reacts really quickly. And it will form rust on its surface, and it'll be a nice bright brick red. And when it forms so quickly, it produces a barrier, right? Oxygen can't get through the layer of rust to the underlying metal, and it'll stop, right? What they didn't count on was Atlanta gets a pretty good amount of rain, between 60 and 80 inches a year. And as soon as we get a big rainstorm, it washes that rust off, and it streaks across the concrete. And it was ugly. So needless to say, that building is not there anymore. They decided to tear it down and put something else up. Now, that concept of oxidation, changing from one substance to another on the surface to protect the underlying material, that's a valid process. And it's the process that makes stainless steel work. Stainless steel has, originally it had 35% chromium in it. The original stainless steel. Now they've got different varieties, but the chromium is extremely reactive in an oxygen atmosphere. And all you have to do is scratch the surface, and at the microscopic level, you would see the chromium and the oxygen instantly reacting and sealing the wound. And of course, when you polish it, it's nice and shiny, because everybody, have you ever seen a chrome bumper? Maybe on some antique cars. Yeah, that's pure chromium on the surface of the steel that's deposited by electroplating. And it's a bright silver, right? And that's why stainless steel, polished stainless steel, looks that way. It's got the chromium in it. Okay, so this is just a flow chart that you can follow, physical property versus physical changes, and another one for chemical. I'll leave that up there long enough for it to be recorded. And when you're looking at these recordings, of course, you can always pause them, right? If you need to pause and study something. Okay, which of the following is an example of a chemical change? Pulverizing rock salt. Did the identity of the salt change? Nope, that's a physical change. Burning of wood. Yeah, you're taking cellulose and lignin primarily. There's some ash in there. I mean, inorganic materials. But when you burn the wood, you convert it to, if it's complete combustion, you convert it to carbon dioxide and water. Right, so you've changed the identity of the substance. Dissolving sugar in water. No, sugar and water, they're the same. And one way you know that they're the same is, how do you get them back? Just evaporate the water, and you got sugar left. If you do it right, you can make rock candy. Okay. Melting a popsicle on a warm summer day. Physical change, right? You still got the coloring in the popsicle. You still got the sugar in the popsicle. You still got the water. It's just kind of, it turned into a liquid now. Okay, let's talk about the difference between pure substances and mixtures. A pure substance is a kind of matter that can't be separated into other kinds of matter by physical means. In other words, we can't use a physical process to simplify it. You can't separate it into different substances. Like if you have distilled water, like it's in this tank right here. If you evaporate that water, what do you got left? Nothing, right? Just the water leaves. It's a pure substance. There's nothing else in there but water. Okay. If we had a solution, a mixture, say we put sodium chloride, table salt in there, and we evaporated that, okay, physical process of evaporation. You get the water separated out as a gas and you leave behind the salt. So now we know it's not a pure substance, it's a mixture. So when you combine two or more pure substances, you get a mixture. Salt water is one example. Now, pure substances could be compounds. They could be combinations of one or more elements, two or more elements, excuse me. You can have a pure substance like water, or you can have a pure substance like gold. If you own some gold bullion, it's usually 99.99% at least pure. That's a pure substance as an element. Or you could have a mixture, right? We talked about one type of mixture. Another type of mixture is one you're breathing, mixture of gases, right? We have oxygen in there. That's the one we depend on. And there's lots of nitrogen in there. 78% of the air you breathe is nitrogen. 21% of it is oxygen. And the other 1% is a combination of argon, carbon dioxide, water vapor, some other things. But that's a mixture. Now, there are types of mixtures. A heterogeneous mixture is one in which sampling the mixture at different locations gives you different percentage compositions for each of the members. It's heterogeneous. It's like if you get a jar of jelly beans, right? You can just look around the outside and you can see, you can count maybe lots of greens over here and maybe a red or two. And then on this other side, lots of reds and only a couple of greens. Okay, that's heterogeneous. It's not uniform. Homogeneous mixtures are uniform throughout. And anywhere you sample that mixture, you will get the same composition. So if we have salt water, I can take a small sample, I can take a large sample, and determine how much water and how much salt is in the sample and ratio them, and the ratio will be exactly the same no matter what size or where you sample. Okay, that's a homogeneous mixture, and in fact we have a name for it. It's called a solution. So solutions can be collections of, let's see, is it on the next slide? That's a decision chart. Solutions can be mixtures of multiple types of phases, right? We combined solid salt with liquid water and made a mixture, a solution. But you can combine gases, right? Make a solution, right? In fact, anytime you put two or more gases together, you always get a solution, always a homogeneous mixture. That's because there's so much room between each of the molecules. At the microscopic level, there's room for everybody. So you always get a solution. You can combine two solids, like two metals together, right? We call that an alloy. That's a homogeneous solution. Which of these are homogeneous mixtures? Pure water? Nope, that's a pure substance. How about gasoline? That's a homogeneous mixture. Primarily octane, the hydrocarbon octane, and some other additives that the petroleum companies want you to think keep your engine clean, maybe, or whatever. Or they may put ethanol in them, ethanol and octane. Jar of jelly beans, we talked about that one already. That's heterogeneous. Soil, take my word for it, soil is heterogeneous. Particle size and composition, other types of composition, it's heterogeneous. If you ever drive by a road cut and look at the layering, it's obvious. The layering in the soil it's usually dark around the top where the organic matter is, where the plants live, and then it changes color underneath, right, as you move down in the soil. It's called the soil profile, but the soil is heterogeneous. It's not a uniform mixture. Copper metal, pure substance, right? So gasoline is the only one of those that is homogeneous. I'm going to have to move on. I'm sorry. So what do we identify as an element? An element is by definition a pure substance that can't be broken down into simpler pure substances by chemical means, right? And during the Middle Ages, alchemists even had identified several elements that were populated into the first periodic table that was produced by Mendeleev. These substances had already been identified, and everything they tried to simplify them, divide them out into different substances, failed. So they concluded that they had an element on their hands. Gold, silver, and copper were some of the first. Gold was easy because gold exists in large part in nature as elemental gold. Right? It's only in sometimes it's in a compound, but most of the time it's pure substance gold. So you can go to Alaska or California and pan for gold. Silver and copper are a little more reactive, so they're usually combined with other things. A compound, on the other hand, is a pure substance that can be broken down into two or more simpler substances by chemical means, which means the compound is a combination of elements, atoms of the elements combined to make a new substance. So hydrogen has its characteristics as a gas, right? Oxygen has its characteristics as a gas, but when you put them together and run a little spark through them or set a match to them, they react and make water. So we've got these two elements that come together to make this compound. Compounds are always combinations of two or more elements, but they are pure substances. All right. So this is just a rehash, compounds versus mixtures. Mixtures can be separated by physical means. Compounds cannot. Compounds have to be separated by chemical means. And in the process, you produce, with mixtures, you produce substances that still had the same identity while they were in the mixture. Whereas with a compound, when you separate parts of a compound, you get new substances with new identities. Oops, it's the wrong button. Okay. This is just a flow chart for classifying samples of matter. I'll leave it up there long enough to be recorded, but we're going to move on. Let's see. All right. How about the elements? There are 118 known elements in the periodic table. Unless you watch science fiction movies and Star Trek and those types. They come across these elements that aren't on the periodic table occasionally, right? Or how about what was Wolverine, right? What was that metal that they put in him? Adamantium. It's not on the periodic table, right? So there are approximately 88 of these elements are naturally occurring, and 30 of them are synthesized, right? So how do we synthesize new elements? In a nuclear reactor, right? Predominantly. You can make them by smashing atoms together in an accelerator, but if you want to make a lot of them, you need to use a nuclear reactor. I think all of the elements that I've got on that periodic table that I want you to memorize are naturally occurring. Yeah, I'm pretty sure they're all naturally occurring. How about the abundance? The atom percent. That is when you count atoms in a sample, in this case, the universe. Most of the atoms in the universe are hydrogen, 91% of them, right? Predominantly because of the stars, right? That's the fuel for stars, is hydrogen. And they make helium, so that's going to be the second most abundant. In fact, helium was first identified in the sun by observing the spectrum of light, the wavelengths of light that come from the sun, and comparing them with known elements. And there was this unknown spectrum. So the person that was investigating it concluded it was a new element and called it helium after the sun. It was only later that helium was discovered on Earth. And you have any idea of where the most abundant source of helium is? Right? Helium's very light. So in the atmosphere, it tends to go out into space. So there's not a whole lot of helium in the Earth's atmosphere. Where do we find it? The best source currently is in natural gas. When you tap a natural gas reserve in the ground, it's going to have some helium in it in much, much higher percentages than the atmosphere. So when you clean up your natural gas, separate out the helium and stash it away. There was a time when helium was considered a strategic element, and the federal government controlled its availability, particularly leading up to World War I. We had the world's largest stockpile of helium, and we said, Germany, you can't have it, right? Because you're a combatant. So Germany had to use something else. So to make their big Zeppelins, instead of using helium, which they couldn't get a hold of, they had to use hydrogen. Now, hydrogen has a greater lifting power than helium because it's a lighter, actually it's a diatomic element, but it's lighter than helium. It's about half the weight. So it has a greater lifting capacity because it's less dense. The problem is hydrogen is reactive, right? So you get the Hindenburg disaster. All you need is a little spark and a leak in one of your gas bags, and up she goes. Or you get the Challenger disaster, right? Where one of your solid rockets springs a leak through an O-ring and burns a hole into your big orange tank on the outside of the shuttle and combines the hydrogen and the oxygen in that big orange tank uncontrolled and kablooey. But hydrogen and helium make up almost 100% of the number of the atoms in the universe. The rest of it is a very small percentage. Now, on Earth, in the Earth's crust, we have a different arrangement here. Most of the Earth's crust is composed of oxygen. Now, I'm not sure if they're counting water there or not. If they are, that explains oxygen in the oceans. Right? Dihydrogen oxide is water. But if they're not, then if they're only considering the crust as the solid part, then most of the oxygen there, some of it could be entrained water molecules. There's a lot of water in the ground, but most of the elements in the Earth's crust are combinations of that element with oxygen. They're oxides of the element. That's why oxygen is probably the major component there. Silicon is second, right? And that's true for soils too. Silicon dioxide. Everybody knows silicon dioxide, right? You've been to the beach, right? You got silicon dioxide all up in your toes. Or if you go in the surf, you get silicon dioxide all in your bathing suit. And you have to go shower all the sand out. That's silicon dioxide. And then the other elements are less common. Okay. Chemical symbols. You'll notice that the chemical symbols are either single letters, single capital letters, or a capital letter and a small letter. This system was proposed, in fact, in the middle 18th, no, earlier than that, 17th century. Researchers, they called them natural philosophers, were scientists. They were working with these elements, but everybody had their own system for identifying the element. They had symbols for the elements. Some of them were pretty weird. So when we decided eventually to standardize them, there were several proposals on the table, and the one that won out was proposed by a Swedish chemist named Berzelius. And it's a good thing he did. He won out because this is the simplest. We used the English alphabet predominantly, and some of the elements have single letters. They're always capitalized. Some of them have two letters. The first one is always capitalized. If you write, let's see, what's a good example? Okay, let's try this one. If you write this, that says to me nothing and nitrogen. I don't know what that one is. Let's try a different one. How about this one? That's boron and oxygen. Whereas there should be another one with a B and a little o. I'm not doing too well here. A B and I is better. If we have B and I, that's bismuth. But if you write it like this, that's boron and iodine. That's a better example. Took me a minute to get there. So if you write the second letter capitalized, it is wrong. If you're used to writing things, I've seen this on lab reports a lot. If you're used to writing only block capital letters, you know, print your everything in block capitals, you don't ever write small letters, then you're in danger of wrong answers, right? Because that second letter has to be small. Okay, so one other thing you'll notice is that a great many of the elements, if you take the name, you can find the letters for the symbols in the name. Like nickel, for instance, Ni, N-I-C-K-E-L, nickel. But there are some that are not related to the English at all. They're related to the Latin for that element. So things like iron, Fe. right? That's obviously nowhere in iron. It's from the Latin ferrum. Actually, I think it's only got one R. Ferrum is Latin for iron or lead, Pb, right? Where do you get Pb from lead? Well, you get it from the Latin. That's probably my favorite. In Latin, plumbum means heavy. So lead is heavy. We call it Pb. There's several like that. Silver is Ag for argentum. Let's see, where's some others? K, the single letter K is potassium, right? From calcium. Must have been outside. Na is sodium for natrum. That's Latin. There's several of them like that in there, and you'll run across them when you start to make your flashcards. Let's see, there's some others. Copper, Cu, that's close, but no cigar. All right. So how about the atom? We talked about what an element is. What's an element composed of? Elements composed is a pure substance, and it is pure because it's composed of only one type of atom. Each element, collection of atoms, and all the atoms are the same, chemically speaking. Okay. They all behave chemically the same way. So if you pick up a little piece of gold, right, it will have probably billions of gold atoms in there, right? They're very small, extremely small. What's a molecule? Right? You have atoms of your element, and if you make a compound, then you have to put different types of atoms together to make a molecule. On that point, there are several elements in that table that you'll notice have a blue background to them. 1, 2, 3, 4, 5, 6, 7. 7 of them that are there. Those 7 are highlighted because in their natural state, at 1 atmosphere pressure and room temperature, they are all diatomic. Right? So hydrogen exists as 2 atoms of hydrogen connected together. Okay, that's the way they exist. So if a word problem says hydrogen reacts with oxygen, and you want to write the reaction out in what I'm going to show you later in subsequent chapter, you better write it this way or it'll be wrong. So hydrogen is diatomic, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They're all diatomic. These are molecules, 2 or more atoms attached to one another to produce a new substance with a new identity. Well, I guess you could say that. And they behave as a single unit. That's a molecule, like a water molecule, 2 hydrogens and 1 oxygen. That's a water molecule. Okay. When we describe them, we can call them diatomic molecule, in which there are 2 atoms. Diatom, that's a diatomic molecule. Okay. This is a triatomic molecule. Di meaning 2, tri meaning 3. Okay. We could have a diatomic molecule of hydrogen and chlorine, like that. Right. So 2 different elements, 2 different atoms bound together to make hydrogen chloride. We could even put more together, like tetraatomic. How would I do tetraatomic? Let's see, ammonia. That's tetraatomic molecule. 1 nitrogen and 3 hydrogens. Okay. Or phosphorus. Now, that's one way to describe the molecule. Another way is the molecule composed of all the same element? The atoms are all the same. That's a homoatomic molecule. So the example there is this chlorine. It's homoatomic because it's only chlorine. There's nothing else in there. Or phosphorus. One form of phosphorus has 4 phosphorus atoms bound together. Or sulfur has 8 atoms of sulfur in that molecule. Those are homoatomic molecules. Heteroatomic have 2 or more different elements, different types of atoms. So this would be heteroatomic, oxygen and hydrogen, heteroatomic. Heteroatomic, right? Hetero means other. Homo means the same. So if we use these examples, those examples there are just generics. Those are all heteroatomic molecules because they have 2 different types of atoms together. But the first one, the A and the B, is diatomic. The second one, B, to its right, is triatomic. And the one in the lower left is tetraatomic, and the one lower right is also tetraatomic. But those are all heteroatomic molecules. Okay. So how about xenon tetrafluoride? Okay. Xenon is what? It's a noble gas, right? It's not supposed to react with stuff, right? That's why they call them noble gases. They don't react, except if you force them. And those bigger ones, the ones lower down, xenon, radon, krypton, they can be forced to bond with some elements. So in this case, we forced it to bond with 4 fluorides, 4 fluorine atoms. So is it diatomic? Yep, it's diatomic. Excuse me, it's pentatomic, excuse me. It's heteroatomic, excuse me. Pentatomic, heteroatomic. Is it an element or a compound? It's a compound, right? There's more than one element in there. Has to be a compound. Okay. Notation, chemical symbols. I think I've got, let me check my hard copy, see what's coming up. This is the longer chapter, so when we get to chapter 2, it should run quicker. In fact, we're almost done with this chapter. No, it doesn't. Okay, so when we write a chemical symbol, there's information that we can put with that chemical symbol. Let's just use, this is a generic. That's a generic symbol. Could be anything. There are 4 positions here that are reserved for information. This position down here is the number of atoms. So a subscript down there will say you have, say, hydrogen. You have 2, 3, 4, 5, however many of the atoms are in that association. If it's combined with something else, you want to put it there. Tells you how many. So H2O says there are 2 hydrogens and 1 oxygen. We never write 1, right? Because if the symbol's there, you got at least 1. If we ionize the atom, if it has a charge, then we put that up there. Negative, -2, -3, -4, plus, +2, +3, plus whatever case. That's where it goes right there. Now, if we're talking about nuclear characteristics, right? how is the atom built? You know, it has protons and neutrons in the nucleus. We put the protons down here. We give that a symbol Z. That's the number of protons. Up here, this is the number of protons plus the number of neutrons. This is the atomic number. This is the mass number. And the mass number is always the total of protons and neutrons in the element. Now, where do you find that on the periodic table? Well, this number is, well, let's see, on that table is in the lower left-hand corner in the red. So over there on the right where it says RN, radon, that's 86. It has 86 protons in its nucleus. How do you find the neutrons? Well, it's a little more difficult because what they have in that chart is not the mass number, it's the atomic mass. And the atomic mass is never a whole number for reasons that I may get to later. But when we write compounds, we put the elements, whatever the element is. Let's do calcium phosphate. Calcium phosphate is something we haven't covered yet. It's a polyatomic ion. In other words, these guys act like a single unit. So they have a 3- charge by themselves, and this has a 2+ charge. So we need 3 of these and 2 of those. And it's okay to write the subscript outside a parentheses. If you got this unit here with the charge is distributed over the whole group, then you need 2 of them. 2 times a -3 is a -6. And then this one is a +2, so 3 times +2 is a +6. And you balance the charges. But the position here says you got 3 calciums, and here you have 2 phosphates. So how many oxygens do you have? You have 8. 2 times 4. And how many phosphorus atoms do you have? 2. Okay. How many atoms of each element are in each one of these? All right. That formula, H2SO4, if you put it in water, that's sulfuric acid. So it's got 2 hydrogens, 1 sulfur, and 4 oxygens. How about, let's see, iron 3 carbonate. You got 2 irons, 3 carbons, and 9 oxygens. Okay, in that formula. Okay. Oh, I think we're toward the end of this chapter, aren't we? Yeah. We're gonna have to skip this. Sorry. I'll leave it up there long enough to be recorded. All right. So there's the answer to that one. We don't have time to go through it. I'm sorry. If I don't get into chapter 2 now, we'll not finish. Now, if I had all day, I'd just keep going until we finish, but I got a class coming in at, let's see, when is my second class come in? 1 o'clock. Oh, well, we might have time. Yeah, I've already said we're passing on it, so true to my word. So that's chapter 1. Any questions or concerns at this point? Need a break? Anybody need a bathroom break? Okay. We got any smokers in here? Good. Don't have to take a smoke break. Okay. Let me take care of this fingernail before it splits. Yeah, some fingers, the nail will be hard, indestructible, and some of them, you get out to a certain length and it splits. I don't understand that. It doesn't happen on every one, just on certain fingers. This is my pinky, and this one does it on that index finger. Who knows? That's a different class. That's Anatomy and physiology, right? Is anybody taking an A&P here? Going to? Okay. That's a good question. So if you're going to take A&P, are you going into nursing? No? No? You just want to take A&P?
I'm looking for,
Oh, okay. Okay. So you got to know something about human physiology. Oh, yeah. Makes perfect sense. You got to take a bunch of math too, don't you? Yeah. Okay. Well, you got a neighbor there that might need some help, right? There was some complaints about weakness in math. Okay, so let me open, let's share the second chapter. Okay, there's chapter 2. Come on, there we go. And let's make a slideshow out of it. There we go. Now we're going to talk about measurements. In chemistry, as in any of the sciences, sooner or later, you got to measure something. Now, we normally, our minds go straight, when we say measurement, our minds go straight to yardsticks, right? Or maybe if we're lucky to, if we're a good cook or we like to cook, measurements go to cups of flour, cups of sugar, I don't know, cups of milk, whatever the case may be. But in chemistry and in the sciences, measurements goes a little bit farther than that. And we have to be, we can't just like go into the chemistry lab like we're going into a kitchen and just start throwing things together, right? I like to do that, but I do that in my kitchen. I don't do it in the chemistry lab. In the chemistry lab, we need to have things a little more organized. So the first thing we need is a measurement system. During the Middle Ages, alchemists, for instance, they had their recipes for doing things, and they taught it to their apprentice, right? Pass it on to their apprentice, but they didn't disseminate that information typically to other researchers, other alchemists. It was a special knowledge. But in modern sciences, we are very dependent on sharing information. The system is designed so that when you make a discovery, in order to retain or build or retain your reputation, you've got to disseminate that information to other scientists so that they can scrutinize it, right? It's called publishing, right? Scientists that are research only forever depend upon the number and types of publications that they have listed under their name. I've got a few, not a lot, but a few when I was in research. And one of the things that we have to agree upon if we're going to publish, if we're going to do the research, we're going to publish our results, is that everybody that reads our report has to understand what we mean when we say a kilogram or when we say a meter. They have to understand what that means. A kilogram is so much and a meter is so long, and there are a whole host of things: mass, volume, length, time, temperature, pressure, concentrations. Those have to be agreed upon units. And there's an international organization that shepherds that or maintains that system. In this country, we commonly use the English system, or sometimes it's called the imperial system. And it's kind of, it's built up over the centuries with very odd units of measure. It's difficult to use, like inches and feet. Like the foot was how long? Well, it depended on who was sitting on the throne, right? Started in England, I think. So the king's foot was the standard length. So the next king that came along was a different length foot. And inches was so many divisions of that foot. The pound was sort of understood, but it was divided into smaller units of ounces. Right? No rhyme or reason for it. Quarts and gallons. A solid ounce of material is different than a liquid ounce of material. So the metric system attempted to solve those problems because in addition to the fundamental units that were established internationally, the subunits were multiples or divisions of tens. In other words, it's a decimal system, which makes things a lot easier to manipulate the values. And what we need is fundamental units. That is, those that are established and agreed upon and maintained at a certain value. So if you have, say, you have a mass of weight that you're going to use on your balance, and you use it to calibrate your instruments, you want to know what is it really relative to the ultimate standard, the fundamental standard. So you take it and you send it to France, and they open up that double bell jar with the kilogram weight inside, and they compare your kilogram to their kilogram, and then they send you a report and tell you how much yours actually weighs. Well, I mean, what is your mass? Right, so they compare yours to their fundamental. So in your textbook, there's a distinction between fundamental unit and base unit. The base unit sometimes is a fundamental and sometimes it's not. So let me explain what I'm talking about here. The fundamental unit for mass. Right? Let's see, fundamental. What I mean by fundamental is that's the mass that is standardized for the universe. And it exists in a cave in France in a double bell jar filled with argon, made out of platinum and iridium alloy. This is the kilogram. Okay. But the base unit for that is the gram. This is the one that's standardized, and this is the base unit because it has a prefix on it, and the prefix is a multiplier. So if you have a base unit and you want to change the size of the unit, you need a prefix of the unit. So let's go with gram again. If the gram is the base unit, and we say 1,000 times, that's equal to a kilogram. Now, why that one? Why did we use a kilogram for the fundamental and not the gram? Well, the gram is really small. If you make a platinum iridium cylinder out of and call it a gram, it's about that big. If you get a fingerprint on it or you scratch it, by percentage wise, you've changed its value significantly. We needed something bigger. So we went to the kilogram as the fundamental, the standardized unit. But the base unit is still the gram. So if we say 1,000, that's a kilogram. If we say 1,000,000 times that, that's a megagram. Right? And the prefix is a capital M. If we want to go smaller, say we go 1,000th of, then that's a milligram. Little m means milli, or 1,000th of. So now we have different units we can play with depending on what we're measuring. If we're measuring something huge, we may want to measure it in megagrams. Or if we're going to measure something that's really small, we'd measure it in milligrams and report the value. So that's for mass. And here's some of the prefixes. G, big capital G is giga, right? Everybody knows gigabytes for computer language, gigabytes. And a capital T is what? Tera, terabytes. So that's G is giga or what's that, a billion. And tera is a trillion, right? So I've got 2 hard drives here that are supplemental to my internal hard drive, and they're both 5 terabytes, right? The first computer I got on the job when I worked for the U.S. Department of Agriculture, and the first computer I got had a hard drive in it that was like this. I pulled it out one time, weighed a ton, and it had 78 megabytes capacity. Now, in something half that size, we get 5 terabytes. The K was the kilo, 1,000 times. D is deci, which is a tenth. C is centi. Centi. Where do we see centi? Centimeter, right? Centimeter. You see that sometimes, centimeter, or you may see it as cubic centimeters, or on medical devices, it might be cc. That's a cubic centimeter. Micro is that Greek letter mu. Micrograms, a millionth of a gram. Or nano, a billionth of a gram. Or nanometers. Yeah, fibers that are on the order of a nanometer are nanofibers, and you may find them in some sportswear. Look on the label. I think by law they have to tell you that they put nanofibers, or it's nanotechnology infused with whatever. That may be the way they get carbon in those, what are those socks and support hose and stuff like that that have carbon infused in them? Copper fit. Yeah, I think copper fit has nano carbon fibers in there. So those are some prefixes and what they mean. They modify the base unit to create a new unit. Okay. Now, the meter, this was for mass. That's mass. Length. The fundamental unit is the meter. It's also the base unit. And the meter was established as a fraction, a small part of the distance from the equator to the North Pole, going along the longitude that runs through Greenwich, England. In fact, it's the 0 longitude. So that distance was determined, and then we're divided in so we get a convenient length, and we called it the meter. And once that was established and agreed upon, then there was a platinum iridium bar with a certain geometry that would keep it from warping. And that bar is also kept in that cave in argon atmosphere. That's the fundamental. It's also the base unit. Nowadays, though, you can, if you have the money and the equipment, you can establish that fundamental length of a meter with your device, because now it's also based upon the number of wavelengths of a particular color of laser light, and your device can fix that length for you. You don't have to go to the platinum bar to establish that as the standard. All right, we talked about the gram already. There's an important point to make here. This is mass. Mass is the amount of something. In other words, no matter where you are in the universe, a kilogram is a kilogram is a kilogram, right? But the weight of that kilogram varies depending on the gravitational field in which it's found. On the Earth, it will have a certain weight. On the moon, it'll have a weight of about 1/6 of that. Okay, so there's the difference between mass and weight. Weight is a force, and it would have a much greater weight on Jupiter. It'd have less weight on the moon, have less weight on Mars. It'd have more weight. Well, the closer it gets to the sun. Okay, the base unit for volume is the liter. But there is no fundamental unit. Well, that's not right. Base unit for volume is the liter. There's no fundamental unit for volume because volume is derived from length, right? The liter derived from the length is 1 cubic decimeter. So we don't establish, we may standardize the base unit, right, for convenience, but it's not a fundamental unit that has been established. It's based upon length, right? Because height times width times depth is volume, right? So if you have a decimeter in length, which is 1/10 of a meter, and you make a cube out of it, that's a liter. But that is the base unit for many expressions of volume, like milliliter. Right? What's a milliliter? Well, a milliliter happens to be equal to 1 cubic centimeter. Right? So if you have a calculation in which involves a cubic centimeter, and you need say it's a liquid, and instead of a cubic centimeter, you'd rather have milliliters, simple. Just change the unit and keep the number. Okay, well, there's the expression. All right, so length, mass, volume, what are we doing here? Oh, okay. This slide is good for one thing. Notice there are equivalent statements in there. 1 meter equals 1.09 yards. When you have an equivalence like that, you can use that information to convert units from one measurement to another. Now, say that bat is a meter long, right? If it's a meter long, then how long is it in yards? You can use that equivalence to tell you how long it is in yards. Did the bat change? No, the bat's the same. The bat's 1.09 yards long. It's also 1 meter long. We just changed the units of measure. We didn't change the physical object. Okay, that's why you can say that they are equivalent, because the reality that they're based upon didn't change. People have a feel for yards and feet, miles. They don't have a good feel in this country for meters, kilometers. But one thing that we do have a good feel for is liters, right? Because everybody's bought a 2-liter bottle of pop or something like that. You know what that volume looks like, okay? You've also bought a gallon of milk, right? Did you know that that gallon of milk is 3.8 liters? Read the label. Does anybody in here ever read food labels? No, most students don't. I mean, I had one in a class in Beckley yesterday. Yeah, she reads labels too. So I'm not as peculiar as I thought I was. I like to know what's in my food, and I like to know things about it, and the label will tell you that. It doesn't always tell you how much of each ingredient there is in that product, because they don't have to by law. They only have to tell you the relative amounts. So if you look at the ingredients, the first ingredient in that list is the largest amount. Okay, so if you get a container of icing, ready-made icing that you're going to put on your cake, read the label. What's the first ingredient? Sugar. Okay. And then sometimes they'll give you an analysis, right? So many calories, so many carbohydrates, and so forth and so on. So let's see if we have a feel for the size of measurements. Which of the following represents the largest measurement of mass of an object? Right? Say the object weighs grams, or micrograms, or nanograms, or kilograms. Which one is the largest? The base unit is a gram, right? Okay, so we look at the prefix. Micro is a millionth of. Nano is a billionth of. Kilo is 1,000 times. So that's the biggest one. Kilogram is the biggest unit in that group. Okay? Try to get a feel for things. I didn't say it before. I probably ought to say it now since I'm thinking of it. Otherwise, I'll forget. Your two best friends in this class, well, in chemistry, are curiosity. You always want to know more about something. And the other is boredom. If you work problems and answer those questions and work lots of problems here and there and get bored doing it, then you're probably going over problems that you've done before and you understand them. So curiosity and boredom go together in this class. If you're never bored, well, that's not a bad sign. But if you are bored, it's a good sign that you're working enough problems, because that's where you really learn chemistry, is when you work problems and try to use the principles that we're introducing here in class to solve problems. That's when you learn chemistry. Okay. What's an exact number? I think this is out of order. Let me check my hard copy and see what's coming. Wait a minute. Yeah, that's right. You know, I may have the wrong. This may be a different set than this. All right, let me skip to the next slide and see if it. Yeah, let's talk about uncertainty first. Uncertainty is ubiquitous in measurements. When you think you've measured something as 96.4 centimeters, that sounds like that's it. It can't be anything else. What you have to realize is that there are various factors that can be introduced into that measurement that introduce error. There's always uncertainty in every measurement. You're never guaranteed that your measurement is the correct one. So what we have to do is manage the uncertainty the best we can. And one of the ways we do that is the way we express the value when we write it. So every scientist will look at your number and we'll see it this way. I'm just going to make something up. 3, 2, 7, 5. So if I write that number, and I leave the units off because we're talking about the number now only, and they look at that number, they're saying, okay, the person who did the measurement and reported this number, they're saying that this is certain. Those digits are certain for that number. This is the uncertain one. It's an educated guess. Sometimes it's pretty good, but it doesn't have to be. When you look at it, you estimate that last one. So whenever you make a measurement, be sure that the last digit in your measurement is the uncertain one, the guess, because that's the way every other scientist in the world is going to see it. Now, as a practical matter, this slide points to how do we know which is certain and which is uncertain when we're making the measurement? Well, if your device is calibrated and you're using a device like this meter stick to measure an object, the one on the left tells you that the length of that green bar is between 3 and 4, right? The 3 has a mark and the 4 has a mark. So those you can consider as certain values. So you have 3 as a certain value, and then you estimate in between 3 and 4. That's your uncertain one. So we estimate 3.7 for the one on the left. But if we go to the one on the right, we also have tenths markings in there. So now the tenths position is certain. And if we go down, if I could blow that up, we would go down to 3.7. It's between 3.7 and 3.8. So we estimate the in between there, and that's the hundredths position, 3.74. We're saying 4 is our uncertain value, a digit in that number. Okay. That's an example of what it looks like in the lab when you're making a measurement. And we'll do that in the third lab, I think it is. We come in here and do some laboratory work. One of the things we'll do is to measure some things. So another way to get a handle on uncertainty is to identify in any number how many digits, how many figures in that number are significant. And the reason we do it this way is down the road, we're going to have to do some calculations with 2 or more numbers. And what we want to do is we want to be able to say, if we know the uncertainty of these numbers in our calculation, what can we say about the answer? How certain can we be about the answer? And that's where significant figures come in. So there are rules, right? Well, I erased the number, so we'll use that one. This number, 3, 4, 5, 6, has 4 significant figures. That's rule number 1. All non-zero numbers, digits in a number are significant. So every one of these are significant. Right? So the next set of rules obviously have to do with zeros, because zeros pop up every now and then. So the rule for zeros depends on where is the zero. In this rule, the zeros are leading. They're on the left-hand side of the number. Those are never significant. And for this number, 0.048, notice that that decimal is explicit. We have to say it's there. If we don't say it there, we don't know where it is. I mean, when you write a number like that, the decimal could be here, right? So we say the decimal is there, and also we don't leave that decimal hanging out there by itself. We don't write it like this. That's what I call an orphan decimal. If you write an answer or a data, a measurement in your report and hand it in that way, it's wrong. It's got to have a 0 on this side to identify it as a decimal point and not the period in a sentence. Okay. I don't want to see any orphan decimals in your answers. So those zeros are not significant. This number has 2 significant figures. Okay, let's move to the right. What if we put a 0 between 2 non-zero numbers? That's called a captive 0 or confined 0. Those zeros are always significant. So this number here has 4 significant figures in it. Okay, so the other zeros are all the way to the right. In this case, the trailing zeros are only significant if there is an explicit decimal point somewhere in that number. In this case, there's a decimal between the 9 and the 3. So that means those 2 zeros to the right are significant. This number has 4 significant figures. Oh, good. I put this one in here. What if you have a trailing zero with an understood decimal, but not explicit? In this case, 150, we assume that the decimal is to the right of the zero, but it's not explicit. So this only has 2 significant figures in it. We're not claiming that the zero is significant. If you meant it to be significant, you got to put an explicit decimal there. In that case, it has 3 significant figures. Okay. Oh, that's a good question. So with these 2 numbers, which one is the uncertain digit? Do I give the answer? Yeah. This one, the 5 is the uncertain digit. The 0 is just a placeholder. So that's certain, that's uncertain. For this one, certain, 0 is uncertain. Okay. All I can say is just memorize it. And the reason I put that in there is when we start to do calculations with these numbers, that fact right there is going to be significant in developing to computing the answer. Okay, so that earlier slide was out of place. Let's go back. Exact numbers. There. An exact number has infinite significant figures. So when it's in a calculation, you can ignore it, except for doing the calculation, of course, but you don't have to count it in determining the significant figures in your answer. Okay. Examples of exact numbers are counting numbers, like 12 objects in a dozen, 9 pencils in the box. Those are all exact numbers. Simple fractions, they're considered to be exact numbers. If you wrote them in decimal form and used them in a calculation, their significant figures would not matter. They have infinite number. Okay, the reason I wanted to get that in there is because we're going to do calculations with them next. How do you do calculations and use significant figures? Well, okay, I forgot this part. We're going to have to be able to round numbers, because what does your calculator do when you punch in numbers? Depending on how many decimal places you set in the register, it'll fill them all up, right? Your calculator doesn't know significant figures. So you have to do that yourself. And it's okay. Keep all those numbers when you write your answer out, but then you have to determine how many of them can I keep in my answer. And to do that, we have to know how to round numbers. So in this example, 3.72456, if we want that to have 3 significant figures, well, you say 3.72, and then you look to the right of the 2, and is the number 5 or greater or less than 5? In this case, it's less than 5. So everything drops off, and you're left with 3.72. You round down. If it's 5 or greater, you round up. So 5.00673 rounded to 3 significant figures is 5.01. Okay, that's the rounding rule that we're going to use. Oops, did you get it? I won't move too fast if you're taking notes. Okay, so when we calculate with numbers and we want to determine how many significant figures we can keep in the answer, there are only 2 rules. One is for multiply, divide, and the other one's for add, subtract. Multiply, divide is the easy one. With multiply and divide, oops, That one's running out of juice. Let's see if I got a spare. Yeah. Multiply, divide. The rule is, no matter how many numbers are in the calculation, as long as it's only multiply and divide, you can multiply, divide all the way out to the end with every one of the figures in your, every one of the numbers in your calculation. And then you go back and look at the numbers that went into the calculation, and you restrict the number of significant figures in your answer to the least number in that group that went into the calculation. So in this case, 6.038 has 4 significant figures, 2.57 has 3. So the answer that we got, 15.51766, has to be rounded to 3. And that rounding gives you 15.5. Okay, so if your calculations only have multiply and divide, even if they're a series of steps, as long as it's only multiply, divide, go all the way to the end and then restrict the number of significant figures. The reason you do it that way is if you have steps, like you multiply and then you divide by another number, and then you multiply by another number, and then you divide by another number. If you round at each step, what if they round up each time? The error at the end is significant. But if you multiply and divide all the way to the end and then round, you avoid rounding error that may be introduced in that process. Okay, and a great many calculations in chemistry are simply multiply, divide. Not to say that there aren't add, subtract, but they're mostly multiply, divide. And that's the second rule. If you got an add, subtract, the procedure is to line up the decimal points of your numbers. So 9.333 plus 1.4, we line up the decimals and we add everything together, right? And we get 10.733. And then we restrict the number of decimal places in our answer to the shortest decimals in the calculation. So we have to stop at 1.4. We have to stop at that 10th position in our answer. And we round it to 10.7. Okay. So what if you have a calculation that's a combination where you have multiply, divide, and add, subtract? Then you have to go to your orders of operation. Remember those from math? Remember that one? Nobody remember? Somebody remembers? So the first is parentheses. Parentheses tell you, if you have them, tell you which operations come first. If you don't have any parentheses, then you go to exponents. You do your exponents. Then you do multiply, followed by divide, and then you add and subtract. That's if the person who presented the problem to you didn't give you any instructions with parentheses. Okay. So notice also, how many significant figures are in the first number? 4, right? 9.333. How many in the second number? 2, right? How many in the answer? 3. So if the question on a test is, in this calculation, how many significant figures are in the answer? If it's an add, subtract problem, you can't just look at the operators and go to the answer. You have to do the calculation to find out how many are in the answer, because 4 in the first, 2 in the second, add them together, 3 in the answer, right? There's no rhyme or reason to it. It's not like multiply, divide. Multiply, divide, all you got to do is say, all right, how many are in the answer? Look at the smallest number of significant figures. There's your answer. And if you have a combination, you got to do the whole thing to answer that type of question. Oh, how about this one? 9333 plus 1400. What's unique about that? Well, what's different about this calculation? There are no explicit decimal points, right? So we line up the understood decimal points, right, to the right of the 3 and the right of the 0. Line them up, add them up. Okay, that's the uncertain digit for that number. That's the uncertain digit for that number. That's where you stop when you round the answer. So the answer calculator says 10733, but you have to round to the position of the 7. And since the number to the right of the 7 is 3, you round down. So it's 107, and you fill in the 33 with 00. Right? You have to put the zeros in there, right? If you don't, then you've changed 10,733 to 107, right? And that would be wrong. So that's what you do with this type of number, where there are no explicit decimal points. Okay. As another practical matter, when you go into the lab and you make a series of measurements on a particular object or an operation of some kind, what is it that determines the accuracy, which we haven't defined yet, but we will, the accuracy of the outcome, right? It's the least accurate device in the sequence that determines. So the cylinder on the left is the one that holds everybody else down, right? It's the least accurate one, less accurate than the one on the right. So if we combine those two volumes, we're limited by the accuracy that comes from the first one. Okay, that's all that means. That's the purpose of that slide. Okay, so I got an extra slide in here that eventually talked about exact numbers. All right, so I'm not going to hammer this one anymore. I will say, though, that in addition to counting numbers and fractions, conversion factors are considered exact numbers. So when you have an equivalence, 1 inch equals 2.54 centimeters, anytime you use that relationship in a calculation, you can ignore the significant figures. Okay. And we're going to talk about that in a minute in a topic called dimensional analysis. Okay, calculator gives you an answer of 8.8274 when you multiply these two numbers. So which one of the answers would you round it to? Well, you look. One of them has 3 significant figures, one of them has 4, so you round it to the 3. And 8.82, 7 is greater than 5, so it's 8.83 is your answer. Okay. Oh, we got a little discussion of exponential versus scientific notation. The nice thing about the metric system is it's all based upon the decimal system. So any changes in size are orders of magnitude, which is another way of saying powers of 10. And that also lends itself well to writing very large numbers or very small numbers in a compact format. Many authors will equate exponential and scientific notation, but they're not the same. Exponential notation only requires that you change your number. Let's see, 1, let's write out that one in standard. 107 fourth power. See, 1, 2, 3, 4. Okay, so this is, actually, I can't do that. So this is the number written out in standard notation. And we could write that as an exponential number. All we have to do is move the decimal point and store up those positions in powers of 10. So we could move 2 places over here and have 107 times 10 squared, right? 10's hundreds. And that would be exponential notation. Scientific notation is a subset of that. Scientific says that this coefficient has to be between 1 and 10. So scientific notation would be 1.07 times 10 to the 4th. That's scientific notation. If we got to say our number was 1,000, it was 10,000, and we moved it over to here, we would have 10 times 10 to the 3rd. That doesn't work because you still got 10 that can be put in this one. So it would be 1 times 10 to the 4th. So if you get to 10, you got to go up in the exponent. So you need to be able to convert large and small numbers into exponential notation and then go backwards, convert the exponential notation into the standard notation. Now I see an error in this one right here. You see it? How many significance numbers, digits are in that 300? Just 1. How many are in the scientific notation? 3. So we've magically added 2 significant figures to that number. What it should have is a decimal point to the right of that 0, the last 0. Then you would be justified in saying 3.00 times 10 squared. But as it is, it should be 3 times 10 squared. That's it. Okay. If you move your decimal place to the left, you are storing up increasing sizes, increasing powers of 10. If you move the decimal to the right in that second number, you're storing up negative values of powers of 10. So that's why the exponent for 10 is -3. And you always need to, when you do this, you always need to ask yourself, is that reasonable? You look at that number, 4.890 times 10 to the -3rd. That should be a small number, right? You look at that -3 over the 10, say, that's got to be a small number. And you look to the left, oh yeah, it's a small number. Right? If you moved it the wrong direction and say 10 to the 3rd, then it should be a big number. It would be 4,890. Then you look over there to the left, oh no, what's wrong with this picture? A small number becomes a large number? No. So when you move the decimal to one side or the other, be sure that you're incrementing the correct either positive or negative powers of 10 when you do it. Okay. Okay, so when you multiply and divide using scientific notation, 2 numbers, say, let's take this number, and we're going to multiply it by 3.7 times 10 to the 3rd. Okay, how do you multiply that number if you don't have your calculator? If you have a calculator, you can put the number in scientific notation in your calculator, and it will do the calculation for you. But if you don't have it, how do we do that calculation? We multiply these 2 together times 3.7, and then times 10 to the 4 plus 3. Then you add the exponents of the 10s, and you multiply the coefficients. Okay? Okay, how do we convert this one to scientific notation? And with only 4 significant figures. Well, you can do it one of 2 different ways. You can convert it to scientific notation first and then round to 4 significant figures. Or you can round to 4 significant figures first and then convert it. It works either way. But it should be 6.30. What do we do with the 1? Round it up, because 7 is greater than 5. 6.301 times, how far did we move the decimal? 1, 2, 3, 4, 5. 6.302 times 10 to the 5th power. Okay. Should I have drawn that on the board? Try it on your own. Okay. Wear a safety harness just in case. Conversion factors. All right. This comes under the heading of dimensional analysis. Conversion factors are a convenient way, actually a reliable way, to convert a measurement that has a number and a unit with it into a different unit so that the number corresponds, right? Because when you change the unit of measure, you're going to change the number, except for one case, right? Milliliters to cubic centimeters. So conversion factors start with an equivalence. In this case, 1 minute equals 60 seconds. So let's get an example. I think an example would work better. Yeah, why does the conversion factor work? Let's say this is your equivalence. 1 inch equals 2.54 centimeters. That's true. Okay. Let's take an example. Say we have so many centimeters. Say you have 70 centimeters, and we want to convert it to inches. Okay, so here's where we're at. There's where we want to be. So we need some way to multiply times that'll give us inches. All right. Well, we know from math that it's legal to multiply any number times 1, correct? Yeah, no big deal. We also know that 1 inch equals 2.54 centimeters. Well, suppose we use another rule. If you have a mathematical equation and you divide both sides or multiply both sides by the same factor, it's still an equation, right? They're still equal. So we're going to divide this one through by 2.54 centimeters on both sides. Okay. I haven't broken any rules yet. Well, what's this equal to? 1, right? Divide a number by itself and you get 1. Notice also that when we do an operation, we have to include the units of measure. In this case, 2.54 divided by 2.54 is 1, and centimeters divided by centimeters cancel out. So now this is equal to 1. Okay, so I'm going to substitute that right here. I can do that because I know this is equal to 1. All right, so let's do that. Okay, in this case, we have 1 inch divided by 2.54 centimeters that we're multiplying by that value. Remember, when you write a number, and in this case with its unit, just write it out. Is it in the numerator or the denominator? It's always the numerator. Just a plain number. It's understood to be divided by 1, correct? Okay. So if this is in the numerator and that's in the denominator, they cancel, correct? Right. Now we're left with the units we want. So all I have to do is divide 70 by 2.54. Well, I painted myself into a corner. I'm going to have to do it now. 70 divided by 2.54, 27.5591. All right. So can I leave it that way? No. That has two significant figures because I put a decimal right there. So we got to round this one to 2. Right? 1, 2, that's a 5. So my answer is 28 inches. Okay. That's why conversion factors work. They're based on an equivalence. And the equivalence is manipulated to equal 1, which we insert in here. So we could say 70 times, if we wanted something other than inches, but we didn't have one conversion factor that would do the calculation for us, you could just chain them together. 1, 1, 1. And plug in here something that would cancel units as you go and leave you with the one you want. That's called a chained conversion. All right. So that's what this slide says. Same thing. I just thought it would make more sense if I did it this way. But there it is in black and white and red. And notice in all these calculations, the units of measure must be accounted for at every step. Sometimes we have calculations where you have a unit, a number and its unit times another number and its unit. And since they're not numerator denominator, they don't cancel. So we have to combine them. So it would be something like, oh, I don't know. There's one that comes out joule seconds. Okay. So notice also that if this is equal to 1, that's equal to 1. 2.54 centimeters divided by 1 inch is also equal to 1. Because if that's equal to 1, you can flip it and it's still 1, correct? Okay. So if we want to convert from inches to centimeters, we just flip it and it would cancel the correct units and leave us with the ones we want. Okay, these are some other conversion factors. 1 pound equals 454 grams, or 1 kilogram equals 2.2 pounds. The problem with that picture is grams and kilograms are mass and pounds is weight. So these conversion factors only work on the surface of the earth, right? You couldn't use that on the moon. Okay, and I make a point here of this at the bottom of this one. 1 milliliter equals 1 cubic centimeter. That's where it would be 1 cubic centimeter divided by 1 milliliter. So it's 1 and 1. So they're essentially equivalent. All right, I'm gonna have to skip that one. These are just some steps that you use, and what we have done here is called dimensional analysis. In other words, the progress of the problem solution is based primarily on the units of measure. We analyze the dimensions, the units. So we start with centimeters, we know we need inches. That means the conversion factor or factors have to enter in such an order that they will cancel the ones we don't want and leave us with the ones we do want. That's dimensional analysis at this stage. Right, and those are the steps that I went through here, just in black and white. Here we go. I'm gonna have to skip that one. I mean, they're useful, right? Exercises, but I think you're going to have several of them in the document that'll give you practice. So we don't have to linger here, particularly since we're running out of time. And I haven't got to the lab yet. This particular problem is if you were going to make a trip from New York to Chicago, actually for me, I make a trip from Beckley to Atlanta to see relatives. So I do the same thing. I want to know how much money do I need to take with me so I can buy gas on the way down and buy gas on the way back? Or how much do I need to have in my bank account so I can slide my card and pay for it? And what you need to know is how far is it? And that has to be converted to how many gallons of gas does that represent? So we need the mileage of your car. And then how much does a gallon cost? When I wrote this one out, it was a lot cheaper. Must have been during the Trump era. But the equivalences you have there and the conversion factors cancel out miles and gallons and leave you with dollars. So that's how much money it would take to go one way. And then, of course, if you want to come back, just double it. And if you want to drive around a little bit, pad it with 10 or 15, 20%, whatever the case may be. If it's a big city, you want to pad it with 20% probably. It's a small town, you can get away with 5 or 10% padding. Okay. So the reason we're going to stop on density here is to emphasize the utility of equations. These are mathematical equations, and this is density. Density is defined as mass divided by the volume of that mass. So it's going to have units, depending on what units are here, and here will be the units of your density. For gases, let's start with solids. For solids, we typically have grams in the top and cubic centimeters in the bottom. For liquids, we usually say grams and milliliters, right? So if you determine it this way, it's exactly the same as that one, because that's equal to that, correct? Gases are so, their density is so low that we need more gas in order to make a measurement. So gases are usually reported as grams per liter, a greater volume. Okay. Another interesting point that I want to make is the difference when you're looking at a measurement. Is that measurement extrinsic or intrinsic? What I mean there is an extrinsic value varies with how much of the material you have. So if you have more material, it's going to have more mass, right? So mass would be an extrinsic property. But if you know that the mass represents a certain amount of volume, and you divide by the volume and you get density, then density is an intrinsic value, which means the value that you determine does not change with the amount of material you have. Why? Because if you have more mass, you've also got more volume. So density is the same no matter how much of the material you have, right? If you have just a little grain of gold, it's density, whatever that is. But if you have a nice big brick of gold, which is preferable, then it has the same density. So that's an intrinsic property. So back to density. In equation, if you know all but one of the values, these are variables, right? If you know this value and that value, you can solve for this value. But if you know this value and that value, you can solve for that value. Right? It's algebra. Any equation in one unknown is solvable. And those are the types of equations that we will use. Only one unknown. We're not going to do simultaneous equations with two unknowns. Right? Does anybody have algebra in here? Algebra. Okay, so you remember, you know what I'm talking about. How do you solve an equation that has two unknowns in it? You don't. Not unless you have another equation with the same two unknowns. Then if they're simultaneous equations, you can solve those too. We're not going to do that. All of our equations, you will have values for every variable except for one, and then you solve for that one. So you can rearrange the equation. You could say, if I want to know mass, and then I have density and volume, it'd be like that. If I want to know volume, and I have mass and density, it would be like that. Or if you have the equation and you have the value for this and that, just plug them in there and then solve for the unknown. Either way works. Unless you're going to use one of these in another equation. If you substitute it into another equation to get an answer, right? Then you would do it this way first. Okay, so I better get a move on. This mineral has a mass of 17.8 grams and so many cubic centimeters. So that would be its density. And notice that the grams do not cancel with the cubic centimeters, so they have to both stay there. Grams per cubic centimeter is the unit of measure for this density. What if we have that many milliliters of liquid and we know the density? Then we want to solve for the mass, right? So in this case, we just plugged in the numbers. Now we're going to solve for the unknown. 42 grams based on that information. Now, anytime you see a question like that, particularly on an exam, of course, what you want to know is, what is the question? Right? If you don't know what the question is, you can't get the answer. So I would advise not to think about what did we study in this chapter, all this stuff we studied, and then take the problem and say, okay, I'm going to take these round pegs and cram them in that square hole. It won't work. You work the problem, you don't work what you studied. I mean, you study for a purpose, but that doesn't dictate the solution to the problem. You studied so that you'll know how to approach the problem. I had a friend of mine at LSU. He was in mechanical engineering, and he said he was surprised at how many students would go into a test, and they're presented with a problem, and they would take the information from the problem, plug it into a formula that they remembered, and write that down as the answer. They wouldn't even check to see, does that answer make sense, right? The answer would have been something like, you know, what's the force of a pull on this bow? You've built a compound bow. What's the force required to pull it back, right? So their answer comes out as 3.5 million pounds. They write it down simply because they did the calculation and said, oh, it's got to be right. But no, it doesn't make any sense. Who's got that much force in their arms? It won't work, right? So think about that, work the problem, know what the question is, and then check yourself to see if you're still in the real world with the answer. All right, so there's the definition of density. Temperatures. We're getting close. You know what we didn't talk about was accuracy versus precision. And I'm not sure if it's in there, because my slide set here doesn't seem to correspond to that one. Okay. Maybe yours does. Do you have a slide in there with targets on them with, do you have one of those? Yeah, but I don't have it in here. So I think I've got the wrong slide set. Accuracy and precision. Accuracy is a measure of how close your measurement is to a true value. Now, since true values are very hard to come by, right? Why? Because of uncertainty. We go for accepted value instead. So once an accepted value is determined for any object or whatever you're measuring, then you can compare it versus accuracy. So when we say, is our measurement or is our collection of measurements accurate? Because usually when you make measurements, you're going to make multiple measurements simply because each measurement is going to be slightly different. And then you take the average. So if we have a target here, and there's your bullseye, and you shoot at that target and you get 4 right there, right? That's accurate. You're right on target. How about precision? Precision is a little easier to deal with. Precision says, how far apart are your measurements spread? Are they way apart or are they really tight? In this case, the precision is also very good. So you got good accuracy, good precision here. What if we did this? We got another target. There's your bullseye, and you had like this. Right? That would be the average of those would be on the bullseye. That would be good accuracy for your measurements, but it would be bad precision because they're spread out too far. Okay. What about this one? What if you had like that? That's good precision because they're grouped, but it's bad accuracy. Okay. Which one do I not have up there? Like that. The average of those would be somewhere in here. So that's bad precision and bad accuracy. This is probably the one we don't want for sure in our measurements. It's nowhere here, nowhere near the accepted value, plus the precision is lousy. Okay. I guess we'll be okay because the lab we were going to do is just the safety document. And you can take that home with you and read it and fill it out. Turn in, there are 2 pages on it that are identical. One is for me to keep and one is for you to keep. And then you also keep the safety blurb in your notebook. Okay, let's talk about temperature. Temperature, is it extrinsic or intrinsic value? Think about it. If you measure the temperature of your body, you get an accurate internal temperature. Is that the same everywhere in your body, no matter where you check it? Usually, if it's done right. Your internal temperature is right, nominally 98.6. Most people are a little less. That's an intrinsic value, intrinsic measurement, because it doesn't change with where or how much you've got of the material. So if you have a temperature of 10 degrees in this little tennis ball, now it wouldn't be good, a golf ball. And then you have 10 degrees measured in this bowling ball, right? Doesn't matter how much it is, it's still 10 degrees. But what we need is a system of measurement. And the systems of measurement that we are familiar with are both, well, in order of creation, the first system of measurement created was Fahrenheit, and then Celsius, and then Kelvin. So let's see. Oh, got the years too. Fahrenheit was 1724. And they were named after the people that created them, right? Fahrenheit created his system because he was working with living systems, primarily animals. And he wanted a range of degree measurements that were within most body temperatures. That's why that's the current range. And that's why 98.6 is really close to 100, which is one of his set points. Celsius was working in the chemical world, in the physics world. And he wanted something that could be more easily calibrated. So his 0 point was 0 degrees Celsius is the freezing point of pure water. And 100 degrees is the boiling point of pure water. And those are very easy to obtain by the chemists of his day. So they could calibrate their thermometers reliably. Once you know where 0 is and where 100 is, subdivide them into 100 marks, and there's your degree Celsius. Kelvin came a little bit later, 1848. The big thing going on at this time was thermodynamics, heat engines in particular. And what Kelvin noticed was that when you try to do calculations with the Celsius system, sometimes you have negative temperatures, right? If 0 is the freezing point of water, there's a lot of stuff that's colder than that, isn't there? And you can't put a negative number into a thermodynamic equation and get a reliable answer. He needed a system with only positive numbers. So what did he do? Well, he took the Celsius system and he just moved the 0 point. From the freezing point of water, he moved the 0 down to absolute 0, right? Nothing colder. So that means every temperature in the Kelvin scale is positive. And that solved that problem. I mean, it's more complicated than that. And I've got a copy of his photocopy of the paper he wrote proposing the system. And the language is kind of hard to follow because in those days, I don't know, they just sort of, their sentence structure was like a mile long. So it's kind of hard to follow. But the point this slide makes is that the temperature is a property of the object. And the temperature varies only because we're using different systems, right? The temperature of the object didn't change at all. It's still got the same average kinetic energy of all the molecules inside, which is the definition of temperature measurement. So the object doesn't change, but the temperature changes because we use different scales. So we should be able to create an equivalence between and among those scales so that they can be interconverted. And I hope that's what the next slide is. Yeah. So since Celsius temperature unit is the same as the Kelvin unit, all we have to do is account for the movement of the 0 point. And that's what K equals C, degree C plus 273. Okay, that's our equivalence formula for that. This is a little more complicated because the Celsius degree unit and the Fahrenheit degree unit are different sizes. So we have to account for that, plus we have to account for movement of their 0 points. So the formula for that one is degrees Fahrenheit equals 9/5 times degrees centigrade, or Celsius, excuse me, plus 32, right? 32 degrees Fahrenheit is where water freezes in the Fahrenheit system, but in the Celsius, it's 0. So that's the adjustment for the 0 point. This is the adjustment for the size of the degree. 9/5. Your book may say 1.8. It's exactly the same number, but this is the way I memorized it. So if you know Celsius, you can convert to Fahrenheit simply by using that relationship. If you know Fahrenheit, then you can plug it in and solve for Celsius. And there's the address for a good explanation of how this was derived. Right. I figured we really don't have time for it now. Only if you're curious enough, go to that website and read about how this formula was developed. This is another one that's fairly easy to follow. Once you know the formula, the relationship of Celsius to Fahrenheit, it's interesting to me, at what temperature would the value for degrees Celsius equal the values for degree Fahrenheit? Is that possible? Right. So how do you do that? Well, mathematically speaking, algebraically speaking, if they're equal, you can make them both the same variable, right? So just call that one X and call that one X. Now you've got an equation in one unknown, solve for it. And that's what we did here. We solve for that, and we find out that at 40 degrees Celsius, you're also at, minus 40 degrees Celsius, you're at minus 40 degrees Fahrenheit. Okay. Now, does anybody know what minus 40 degrees Fahrenheit feels like? No. You ever been to, where's it, International Falls, Minnesota? I think it even gets colder up there. Well, I know what minus 40 feels like. I used to work in a hotel restaurant supply house. So we had dry goods and we had fresh foods, meats. We butchered our own meat. And we created, for some of our customers, we created frozen products, like hamburger patties. I can still hear the hamburger patty machine clanking in the background. And what we would do is, once we made those patties or any of the other products, we wanted to freeze them quickly, because the quicker you freeze them, the better the product when you thaw it out. So we had a freezer, we call it a blast freezer. It was minus 40 degrees Fahrenheit. And you just put those things on the rack, slide them in there, in 10 minutes, they're solid as a rock. Okay. The bad part for me was I was a part-time worker. I was a student at the time. And that put me, I'm on the bottom of the totem pole. So every month, inventory time would come around. So guess who got to do the minus 40 degree inventory? Yeah. Well, they were nice to us. We come in at like 3:30 or 4 o'clock, and they'd feed us a high calorie breakfast from our stores: sausage, bacon, eggs, biscuits, gravy. It was great. I thought it was great. And I'd go in there for suit up in my big quilted stuff and hat and gauntlets and a big pencil that I could hold and on my clipboard, and I'd do the inventory for about 10 minutes. And then I'd come out into the cooler section and warm up and go back in until I got it done. Okay, so it's very cold. So how about significant figures and temperature readings? Well, it depends on your thermometer, right? Our student thermometers, I think, are only good to 1 degree. So you have to estimate the tenths position. But there are some thermometers that are calibrated in tenths, and you can estimate the hundredths position. That is, they have markings for the tenths. Those thermometers are like this long. Or better yet, you have electronic thermometers. And I have, I think I've got one in storage, and I can bring a couple from Beckley when we measure temperature. And that way you won't have to use the student thermometers, if I can remember to do that. I guess I won't assign buckets today because everybody's not here. So if we can get most of everybody in the class here, or maybe after the second week, or maybe the third week, by then we'll find out who's going to stay with the course. Then we'll split up into teams. Because the safety and the graphing exercise, they're independent. You don't need a partner for those. Okay. Yeah, I think we're close to the end. This question is a good one. My son has had developmental issues when he was growing up, and is determined that he was on the autism spectrum. They called it pervasive developmental disorder, NOS, not otherwise specified. So they didn't know where to put him, so they called it that. Anyway, one of the drugs that he was given along the way, they tried with him, was trazodone. And in fact, that was the one they gave him when he spent a year at a residential facility near Chicago, because he really, hormones hit him hard, and he was dangerous to himself and his parents. So he spent a year up there until he came out of puberty. And one of the drugs they wanted to give him was trazodone, and it calms them down, but it's kind of like what's that drug that they give people in hospitals, just to zombie them out? I can't remember what it's called. Well, anyway, that's basically what it did. I mean, it just knocks you down. Well, this problem says if an individual took 300 milligrams of trazodone each evening before bedtime for a whole year, how many pounds of trazodone would he or she consume? So this is a problem that has several steps in it. So when you find a complex problem like this, you need to break it apart. First of all, of course, you need to know what the question is. How many pounds of trazodone? So we're looking for, the answer is going to be in terms of pounds. We're going to have so many pounds of trazodone as our answer. Where's our starting point? Well, 300 milligrams of trazodone a day. We could start there. Milligrams of trazodone per day. Okay. Now we want to get from here to here. What we want to do is, right, there's no time factor over here. Unless we want to say it's that many pounds per year. We could say that many pounds per year. So we want to convert days to years, and we want to convert milligrams to pounds. When you have a conversion where you're going to convert more than one factor, then do one of them at a time, because they're going to be multiplied all the way across, and you can do them in any order. So if we convert milligrams first, how about milligrams to pounds? Well, what do we know? What's the relationship? We know that 454 grams equals a pound, right? That's one of our equivalents. So if we convert milligrams to grams, then we have access to that conversion factor. So we want to have milligrams down here to get rid of that, and grams up here. So how many milligrams in a gram? Well, if 1 milligram is 1,000th of a gram, it takes 1,000 of them, doesn't it? 1,000 milligrams in a gram. Okay, so we got rid of the milligrams. Now we got grams. Now we can convert grams to pounds. 454 grams per pound. Got rid of the grams, pounds. We're good there. Okay, we got that unit done. This is the thinking part of the problem. Now we want to do time. Right? How many days in a year? On average, 364. We could say 364.25, right, to include leap years. Or is it 365? It's 365, isn't it? So 365.25 in a year. So we got rid of days. So now we got pounds on top, years on the bottom. And that's the thinking part. The rest is number crunching. So you just crunch the numbers. And then since this is all multiply or divide, then these are conversion factors. They don't count. We just need 3 significant figures in our answer. Okay. And to save time, let's just skip to the answer. Oops. 0.241. 0.241, 3 significant figures, pounds in that year. Okay. Practice, practice, practice. It'll get easier with practice. Okay. Oh, we got another one here. If you were given a pound of feathers and a pound of lead, the density of each would be the same, because it wouldn't be the same, right? The density is different for feathers and lead. You got the same mass, but a pound of lead would be like this, and a pound of feathers would be like fill half the room, right? So they wouldn't be the same, they'd be different. And they'd be different because they have different volumes, right? By the definition of density, if they've got the exact same value there, then the volume is what makes the difference in density. Right? Feathers have more volume. Okay, so the answer should be that one. Now, the goal, nominal goal for taking this course is to learn chemistry, right? But I've got another objective. What I want out of you is not just to learn chemistry, but to become clear thinkers. If you can think clearly, that's an advantage that goes beyond chemistry. When you walk into the voting booth, how do you know which selection to make? You say, oh, ooh, I like that name. Check that one. No, you don't want to do that. You want to know what the person stands for, because they're going to represent you, right? So only clear thinkers can do that, right? Many of the powers that be in Washington and in Charleston, and maybe in your city councils or school boards, they hope that you're an indiscriminate voter and that you will vote for them because you recognize their name. But that's not a good way to vote. You want to know something about the person. You want to know what their issues are, what they believe in. And that takes clear thinking. And hopefully learning chemistry will help you work toward that. And I would also hope that most of your instructors have that as an objective in the background also, because chemistry is not the only way to be a clear thinker, but you can even learn to think clearly in English, right? How to structure your sentences, how to structure a paragraph and argue in an essay for your point, right? And learn how to detect logical errors, right? That's something that's not taught anymore, I don't think. You know, logic, how to detect one of the most common logical errors that are perpetrated on the public today are straw man. A politician is asked a question and they don't answer that question, they answer a different question. Or they set up a hypothetical that has no bearing on the problem and they knock that straw man down, right? So it's a disingenuous technique. Okay, any questions? Yeah, that's it. So you got your the safety document, turn it in next week. The graphing techniques, well, we got 15 minutes. You know, I could say a few words about graphing techniques. Let me stop the share. Or we could we could use our time next week to talk about it, so it'll be fresh in your mind. You know, it might make more sense, and you may have some more probing questions about graphing techniques if you read the document first. And then when you come to class, ask your questions. Right. Some of you, if you've done graphing before in a Cartesian system, then this will be old school. But maybe, yeah, read it before you come to class next week, and along with chapter 3. Read chapter 3. And then we'll go through chapter 3, and then we'll have enough time, I'm sure, to talk about graphing techniques, and you can do that here. And you don't have to finish it that day, next Friday, right? It's not due until the following Friday when we